China is building projects so massive and so complex. They left the United States wondering how their projects are even possible. From mind-bending undersea tunnels to mountains split open for record-breaking railways, these megaprojects are rewriting what's possible in Chinese engineering. In this video, we'll uncover insane Chinese megaprojects that America could only dream of building. Let's travel over to Guizhou province, where China is building a megaproject so daring, so dangerous, that most countries wouldn't even attempt it, especially not the United States. Scheduled for completion by the end of 2025, this monumental suspension bridge is set to become the highest tower in the world, standing 625 meters above the Beipan River. To give that some perspective, that's taller than 5 Statues of Liberty stacked on top of each other. The Huajiang Grand Canyon Bridge is a transformative project aimed at revitalizing a remote region and enhancing connectivity. By dramatically reducing travel time across the canyon from approximately 70 minutes to just over 1 minute, the bridge is set to boost economic integration between neighboring cities, such as Guiyang, Anshun, and Qianxinan. The bridge is envisioned as a major tourist attraction, with plans for a center dedicated to extreme sports at the canyon's base. The bridge spans a total length of 2,890 meters, featuring a main span of 1,420 meters, supported by 2 towering pylons, measuring 262 meters and 205 meters in height, respectively. This design not only facilitates the impressive height of the bridge, but also ensures structural stability over the deep canyon. The deck is designed to accommodate 4 lanes of traffic, significantly improving transportation efficiency in the region. With an estimated budget of approximately £227 million, the Huajiang Grand Canyon Bridge represents a substantial investment in infrastructure. The United States can build long bridges, but this is vertical madness. The terrain is steep, remote, and filled with geological challenges. China didn't just take on the challenge, they aced it. The construction of such a high-altitude bridge necessitates advanced engineering techniques and specialized equipment. The primary load-bearing structure comprises 93 segments, collectively weighing around 22,000 tons. Heavy lift cranes and precision engineering are employed to assemble these massive components at dizzying heights. Additionally, the project incorporates state-of-the-art wind-resistant designs to ensure stability against strong canyon winds. The main structure of this $280 million bridge in January 2025 has been completed, marking a significant milestone in the project. The final steel reinforcement, weighing 215 metric tons, was installed, bringing the construction to approximately 80% completion. The remaining work focuses on installing panel segments between the trusses and finalizing the deck. Next up, we have to talk about the Tian Shan Shengli Tunnel, a project that boldly slices through the snow-covered Tian Shan Mountains in Xinjiang. This tunnel, stretching 22.13 kilometers, stands as the longest expressway tunnel in the world, piercing through the formidable Tian Shan Mountains to connect northern and southern Xinjiang. The Tian Shan Range, often called the Mountains of Heaven, is no place for casual construction. These peaks are towering, glaciated, and seismically active. Temperatures plunge to minus 40 degrees Celsius, and avalanches are as common as snowflakes. But that hasn't stopped China from digging a 22.1 kilometer long double-bore tunnel right through it. By comparison, the longest road tunnel in America, SR 99 Tunnel in Washington State, is just 3.2 kilometers long. That's 7 times smaller than what China is pulling off here. Initiated in April 2020, the tunnel is a critical component of the Urumqi-Yuli Expressway, which spans 319 kilometers. The expressway aims to cut the driving time between Urumqi and Yuli County from about 7 hours to just over 3 hours. The tunnel itself is designed as a dual-direction 4-lane passage with a design speed of 100 kilometers per hour. Situated at an average altitude exceeding 3,000 meters, the tunnel navigates through complex geological formations, including 16 fault zones, making its construction a remarkable engineering milestone. With an estimated investment of approximately $3.7 billion, the Tianshan-Shengli Tunnel is a catalyst for regional development. The tunnel is part of the G7 Expressway, one of the strategic mega highways in China connecting its eastern coast to western Xinjiang. Once complete, the tunnel will cut travel time through the mountains by 90%, enabling faster logistics, military mobilization, and trade movement. It's also a symbol of unity, stitching the central and border regions of China closer together, both economically and culturally. The construction of the tunnel employed innovative methods to overcome the challenges posed by the harsh environment and complex geology. A 3 holes and 4 shafts approach was utilized, involving the excavation of a central pilot tunnel flanked by 2 main tunnels. This method allowed for simultaneous work on multiple fronts, significantly accelerating the construction timeline. Specialized tunnel boring machines were deployed to navigate the hard rock and high ground stress conditions, marking the first use of TBMs in Chinese road tunnel construction. The tunnel is expected to be operational by 2025, driving a new era of connectivity for the region. Let's talk about the Yarlung Zangbo River hydropower project, possibly the most controversial and ambitious dam the world has ever seen. Situated in Medog County, Tibet, this project is set to become the largest hydropower facility in the world, surpassing China's own Three Gorges Dam in both scale and capacity. The Yarlung Zangbo River, which flows through Tibet, eventually becomes the Brahmaputra, one of the most vital water sources in South Asia. It runs through one of the deepest canyons on Earth, the Yarlung Zangbo Grand Canyon. This location is so extreme, so remote, and so fragile that no country has ever dared touch it, except China. The proposed hydropower project aims to harness the immense energy potential of the river, particularly in a section where it experiences a dramatic 2,000-meter drop over a 50-kilometer stretch. This natural feature presents a unique opportunity for hydroelectric power generation, with the project expected to produce approximately 300 billion kilowatt-hours annually, 3 times the output of the Three Gorges Dam. Grand Coulee was once the largest in the United States, but it's been around since the 1940s. No new major hydro dams have been built there since the 1980s due to environmental pushback and indigenous land rights. China, however, powers ahead with megawatts in the millions. Approved in December 2024, the project is spearheaded by the Power Construction Corporation of China. With an estimated investment of approximately $137 billion, the dam will boast a planned capacity of 60 gigawatts, making it the most powerful hydroelectric facility globally. The construction involves diverting the river through a series of tunnels and installing multiple turbines to capitalize on the steep gradient of the river. The design of the project includes advanced engineering techniques to manage the challenging terrain and high seismic activity in the region. Given the scale of the project and the challenging environment, construction will employ state-of-the-art machinery and techniques. This includes tunnel boring machines for creating diversion tunnels, high-capacity cranes for assembling large components, and advanced monitoring systems to ensure structural integrity in the seismically active zone. Using artificial intelligence, they're simulating 100 years of climate and river behavior before laying a single foundation. The preliminary site preparations have commenced in 2025. The project is expected to be constructed over the next 15 years, with phased dam and turbine installations beginning by 2026. It has already garnered international attention, with downstream countries like India and Bangladesh expressing concerns over potential impacts on water flow and ecological balance. Let's travel over to Liaoning, where China is literally reclaiming the sea to build the Dalian Jinzhouwan International Airport. Situated on a 21 square kilometer artificial island in Hangzhou Bay, this ambitious megaproject is set to redefine aviation infrastructure and bolster regional connectivity in Northeast Asia. Denver is the largest airport by land in America, but it took over a decade and faced constant budget battles. No airport in the United States has been built offshore or reclaimed from the sea. In terms of automation, this airport still lags far behind the smart airport technology China is implementing. Dalian, a strategic port city with a population exceeding 6 million, has long served as a vital economic hub in northeast China. The existing Dalian Qingshuihe International Airport, operational since 1924, has reached its capacity limits due to surrounding urban development and challenging terrain. The airport will feature 4 runways and a 900,000 square meter terminal, capable of handling up to 80 million passengers and 1 million tons of cargo annually. This capacity will not only alleviate congestion at the current airport, but also position Dalian as a major international aviation hub, enhancing trade and tourism with neighboring countries like Japan and South Korea. The project is being executed in 2 phases. The first phase includes the construction of 2 runways and a 400,000 square meter terminal, designed to handle 31 million passengers and 650,000 tons of cargo per year. The second phase will add 2 more runways, expanding the airport's capacity to 80 million passengers and 1 million tons of cargo annually. The advanced land reclamation techniques are being employed to construct the artificial island, involving the use of millions of cubic meters of sand and rock to create a stable foundation. The airport's design incorporates state-of-the-art technology, including AI-powered air traffic management systems, biometric security measures, and renewable energy sources, like solar panels, to minimize environmental impact. The total estimated cost of the project is approximately $4.3 billion. Construction involves the use of specialized machinery for land reclamation, deep foundation treatment, and the assembly of large-scale structural components. Currently, the project is advancing steadily with ongoing land reclamation and foundational work. While initial plans aimed for completion by the end of 2025, the timeline has been extended, with the airport now expected to be fully operational by 2035. Let's move over to Guizhou province, where China has built something that not only outshines anything in America, but literally listens to the edges of the universe. This 500-meter aperture spherical telescope, also known as Tianyan, or Sky Eye, is located in the Daodang Depression in Pingtang County, Guizhou province, China. To put that into perspective, you could fit 30 football fields inside its dish. The sensitivity is 10 times greater than that of the now-defunct Arecibo Observatory in Puerto Rico, which once stood as the American pride in radio astronomy. Now, Arecibo is gone, and FAST stands alone, unmatched, undisturbed, and unstoppable. FAST serves as a pivotal instrument in the quest to understand the universal mysteries. The telescope can detect radio signals from over 13 billion light-years away. That's close to the edge of the observable universe. This includes pulsars, black holes, fast radio bursts, and, possibly, even signals from intelligent life. By joining international efforts like the Breakthrough Listen initiative, FAST underscores Chinese commitment to contributing to global scientific megaprojects. The construction of FAST commenced in March 2011 and reached completion in September 2016. The telescope features a 500-meter diameter dish composed of 4,450 triangular panels, forming a vast, adjustable parabolic surface. This design enables the telescope to focus on different areas of the sky by altering the shape of its reflective surface, a feat achieved through a sophisticated system of actuators and cables. The feed cabin, suspended above the dish, can move to various positions, allowing for precise targeting of celestial objects. The total investment for the FAST project was approximately $180 million. The construction required innovative engineering solutions, including the development of a dynamic support system for the feed cabin and the implementation of an active surface composed of thousands of panels. These technological advancements ensure the ability of the telescope to maintain high precision and sensitivity in its observations. In recent years, FAST has achieved significant milestones, such as the discovery of over 500 new pulsars, enhancing our understanding of these enigmatic celestial objects. The telescope has also detected fast radio bursts, contributing valuable data to this emerging field of study. To further augment its capabilities, construction began in 2024 on the FAST core array, an extension comprising 24 additional 40-meter antennas within a 5-kilometer radius of the main dish. This expansion aims to improve the resolution and mapping abilities of the telescope, solidifying its status as a leading facility in radio astronomy. But just wait until you hear about the Hainan Free Trade Port, a mega project that's not made of steel and concrete, but economics, law, and global trade domination. This free trade zone is an entire island being turned into a free trade powerhouse with ambitions to rival global giants like Hong Kong, Singapore, and Dubai. Backed by the Chinese central government, this project represents one of the most ambitious economic experiments in modern history. The vision for the Hainan Free Trade Port was officially launched in June 2020, when China released a master plan to transform the entire island of Hainan into a world-class free trade port by 2035. But major construction, policy deployment, and infrastructure development are expected to wrap up by 2030. That's when the island is supposed to be fully open for global trade with zero tariffs, streamlined customs, and global business standards. Spanning over 35,000 square kilometers, the HFTP is larger than Belgium, and it includes urban infrastructure, smart cities, seaports, airports, industrial zones, and research hubs. More than 100 infrastructure projects are under construction, including high-speed railways, new airports, and logistics centers aimed at interconnecting the economy of the island. The core objective is to create a global trade hub with low tax rates, digital customs systems, and a regulatory sandbox for cutting-edge industries such as blockchain, biotech, and smart manufacturing. The island will also become a visa-free zone for citizens from over 59 countries, enabling a massive boom in tourism, retail, and real estate. In terms of construction, this is a marathon of megaprojects. New deepwater container ports in Yangpu, offshore oil and gas terminals, and massive urban developments are being fast-tracked. The Yangpu port expansion alone is being equipped with automated cargo handling cranes, smart logistics systems, and blockchain-based customs clearances, a tech-forward strategy aimed at eliminating inefficiencies and corruption. Miami FTZs are small, bureaucratic, and traditional. Moreover, the United States lacks a unified, tech-integrated free trade port model. Hainan Free Trade Port is designed to attract global corporations, while US zones are seen as outdated. The estimated cost of the full-scale Hainan Free Trade Port development is around $5.8 billion, combining government stimulus, private investment, and foreign direct funding. In 2025, nearly half of the planned infrastructure is either under construction or nearing completion. By 2035, Hainan will be a zero-tariff, zero-barrier, fully open trade hub with no import taxes, no capital flow restrictions, and seamless global market access. Next up, we have to talk about the Sichuan-Tibet Railway, a project that makes the American rail systems look like nothing. This is a 2,000-kilometer marvel racing across one of the most treacherous and geologically active regions on the planet. With completion targeted in the early 2030s, major sections of this railway are currently under construction in 2025, marking it as one of the boldest transportation projects in modern Chinese history. The United States has no high-speed rail line like this, and may never finish the California High-Speed Rail project, nearby soon. Meanwhile, China is already connecting extreme terrains in record time. The Sichuan-Tibet Railway is designed to link Chengdu, the capital of Sichuan province, with Lhasa, the capital of the Tibet Autonomous Region. Once complete, the railway will cut travel time between the two cities from 48 hours to just 13 hours. But what makes this route so insane isn't just its length, it's the extreme environment it has to conquer. The railway will traverse earthquake zones, permafrost regions, landslide-prone valleys, and altitudes exceeding 5,000 meters. These are construction conditions that most engineers would call impossible. The route is split into three sections: the Chengdu-Ya'an line, which is already operational, the Ya'an-Ningqi section, currently under rapid development, and the final stretch from Ningqi to Lhasa, which will be the most difficult due to its harsh terrain and fragile ecosystems. What's shocking is that more than 75% of the route requires tunnels and bridges, including the world's highest railway bridge, suspended over deep canyons carved by the Yarlung Zangbo River. The budget for the project is expected to exceed $47.8 billion, making it one of the most expensive railways ever constructed. Construction techniques include laser-guided excavation, artificial intelligence-based stability prediction, and modular bridge components prefabricated in safer environments and then helicoptered into remote, high-altitude zones. This is because the railway climbs to such extreme elevations, and the trains will feature pressurized cabins similar to airplanes to protect passengers from altitude sickness. In 2025, much of the Ya'an-Ningqi section is deep into excavation, with dozens of tunnels and suspension bridges under simultaneous development. Crews are working around the clock, often in oxygen-depleted conditions, using robotic machinery and drones to assist with precision engineering. The full line is expected to be complete by 2030, though some sources suggest it may be finished even sooner. The Sichuan-Tibet Railway is proof that no mountain is too high for modern megaprojects, literally. Let's talk about the Chengdu Tianfu International Airport, a project completed with such scale and speed that US aviation experts are still in disbelief. Located approximately 51 kilometers southeast of downtown Chengdu in Lujia Town, Jianyang, this airport is all set to redefine air travel in China. This airport is a strategic piece in the national dual hub plan, placing Chengdu alongside Beijing, Shanghai, and Guangzhou. Chengdu Tianfu International Airport officially opened in June 2021. But don't be mistaken, the megaproject is still expanding rapidly, with full-scale completion anticipated by 2030. The airport is being constructed in 3 phases, with Phase 1 already completed, consisting of 3 runways and 2 terminal buildings covering a massive 710,000 square meters. Once fully complete, the airport will have 6 runways and 4 terminals, capable of handling 120 million passengers and 2.8 million tons of cargo annually, ranking it among the largest airports in the world by capacity. The design of Chengdu Tianfu is also a standout feature. The terminal's architecture is inspired by the sun god bird, an ancient cultural symbol of Chengdu, making the airport not just a transit hub, but a cultural showcase. The futuristic, flower-shaped terminal was designed by Zaha Hadid Architects in collaboration with China Southwest Architectural Design and Research Institute. It prioritizes green technology, natural light, and intelligent passenger flow systems to optimize energy usage and reduce carbon emissions. Construction techniques have matched the scale of the ambition. Massive amounts of high-performance concrete were poured using automated batching systems, and prefabricated steel modules were craned in using GPS-guided machinery. China deployed BIM throughout the construction lifecycle to ensure accuracy, minimize delays, and integrate various engineering subsystems. Meanwhile, automatic baggage handling, AI-driven security screening, and robotic cleaning systems are being installed to improve efficiency and hygiene. In terms of budget, Phase 1 alone cost over $10 billion, and with additional expansions, the entire project is expected to cost upwards of $30 billion by 2030. The airport is also directly connected to the city via high-speed rail, metro lines, and expressways, forming a multimodal transportation hub that reflects the nation's larger infrastructure modernization push. Currently, the expansion for Terminal 3 and Runway 4 is underway, with completion of Phase 2 expected by 2027, and final construction aiming for 2030. Airlines including Air China, China Eastern, and Sichuan Airlines have already made Tianfu a major hub, with increasing international routes being added as travel demand grows post-pandemic. Next up is the Dalian Bay Undersea Tunnel, a 5.1-kilometer engineering wonder buried beneath the sea. With completion expected by 2030, this incredible megaproject is one of the most ambitious underwater road tunnels ever attempted in Asia, and perhaps the world. Located in Liaoning province, this tunnel will stretch 5.1 kilometers beneath the Dalian Bay, linking the Zhongshan district to the Ganjingzi district of Dalian. Constructing a tunnel under the ocean isn't new, but building one that navigates seismic fault lines, soft seabeds, and coastal city congestion while maintaining high traffic flow is a different beast entirely. The tunnel features 6 lanes of traffic, 3 in each direction, and is designed to accommodate high-volume, high-speed travel under challenging marine conditions. With its alignment crossing complex geological formations, including deep sediment and strong tidal currents, the project has faced serious engineering hurdles. But thanks to the use of immersed tube tunnel construction techniques, China is pushing the boundaries of what's possible. The construction involves segmental, precast concrete tubes, each weighing several thousand tons, manufactured onshore and floated out to sea. These segments are then submerged, aligned precisely, and connected underwater with high-pressure seals and hydraulic jacks. The deep seabed dredging, precision alignment systems, and custom-built floating caissons represent some of the most advanced tunnel engineering technologies in the world. The Dalian Bay Undersea Tunnel carries an estimated price tag of over $2 billion and has employed thousands of workers and engineers over the course of its timeline. Work officially began in 2020, with full-scale segment placement starting in 2022 and finishing touches expected by early 2030. Despite marine construction challenges, storm delays, sediment shifts, environmental approvals, China is hitting its targets. Now compare that to the United States, where the Gateway program, a new Hudson River rail tunnel, has been stuck in political limbo since 2009, and even till date, construction hasn't started. Once finished, it will become one of the longest and deepest immersed tube tunnels in China, easing chronic traffic congestion in the coastal city, while cutting travel time across the bay from 40 minutes to just 5 minutes. The tunnel is expected to revitalize the local economy, boost logistics between port facilities and inland urban zones, and form a key part of the Dalian Port Development Strategy, turning the area into a key logistics and shipping hub in Northeast Asia. Let's move over to Shanghai, where China built the Yangshan Deepwater Port, a port so massive, so futuristic, it could pass for a science fiction movie set. Located near Shanghai, Yangshan Port is built on islands connected to the mainland by a 32-kilometer sea bridge, the Donghai Bridge, another megaproject on its own. The significance of Yangshan Port cannot be overstated. It's part of the Shanghai International Shipping Center, designed to transform the city into the largest maritime hub in the world. With global supply chains constantly evolving, this port offers unmatched depth, capacity, and automation that positions it to handle the future of shipping. Sitting on Yangshan Island, which was previously unreachable, this project involved one of the most extraordinary feats of modern infrastructure, connecting the port to the mainland via the Donghai Bridge, a 32.5-kilometer marvel that stands as one of the longest cross-sea bridges in the world.
Next up, it's time to investigate the Hangzhou Bay Bridge. The project is a massive transoceanic structure that spans 22.4 miles across the Hangzhou Bay in China, connecting the cities of Shanghai and Ningbo. The bridge was designed as a cable-stayed structure, which is common for projects of this scale due to its efficiency in managing large spans. The main span, measuring 1,469 feet, was engineered to allow large vessels to pass underneath. One of the most significant challenges the project encountered was the bay's notoriously strong tidal flows and high levels of seismic activity. This forced engineers to adopt advanced solutions to anchor the structure securely and ensure its long-term stability. The seabed of Hangzhou Bay consists of loose sediment and soft soils, making it unstable for standard foundations. The bridge needed an advanced piling system to ensure it could withstand the powerful tides and seismic forces. Engineers opted for deep-driven piles, some of which extended over 200 feet below the seabed. These piles were driven deep into the earth to reach solid layers of rock that could provide a more stable foundation for the structure above. The piles were made of reinforced concrete and were driven into the seabed using large hydraulic hammers, a challenging operation in the constantly moving waters of the bay. Additionally, steel piles were used in some areas to provide additional strength. To protect these foundations from the corrosive effects of salt water, cathodic protection systems were installed. These systems prevent electrochemical reactions that cause corrosion by introducing sacrificial anodes, which corrode in place of the structural materials. The Hangzhou Bay Bridge uses both pre-stressed concrete and steel girders in its superstructure. The decision to use these materials was largely due to their durability in marine environments and their ability to support heavy loads. The concrete was pre-stressed to improve its tensile strength, which was vital given the length of the bridge and the loads it needed to bear. The bridge deck was constructed using modular prefabricated sections that were floated out to the site and lifted into place. Each section weighed several hundred tons, and their precise placement was critical to ensure that the bridge aligned correctly as construction progressed. The amount of prefabricated sections helped speed up the construction process and reduce the amount of work that needed to be done in the harsh conditions out on the water. Specialized cranes were used to lift these sections into place, and GPS positioning systems ensured that they were installed with millimeter precision. The sections were joined using high-strength steel tubes and reinforced with additional steel girders to ensure their stability. The use of modular sections also made it easier to install the necessary expansion joints, which allow the bridge to expand and contract with changes in temperature without causing damage to the structure. The pylons of the Hangzhou Bay Bridge rise hundreds of feet above the water and are made of high-strength steel and concrete. The cables themselves are made of thousands of individual steel strands bundled together to form a cable capable of supporting enormous loads. Each cable was carefully tensioned to ensure that the forces acting on the bridge were evenly distributed. One of the key challenges in the construction of the cable-stayed section was managing the forces acting on the bridge as each new section was added. As the bridge deck was extended out from the pylons, the cables had to be carefully tensioned to prevent the deck from sagging or becoming unbalanced. Engineers used sophisticated computer models to predict the forces acting on the bridge at each stage of construction and to adjust the tension in the cables accordingly. Given the seismic activity in the region and the exposure to strong winds, the Hangzhou Bay Bridge had to be designed to withstand both earthquakes and high wind loads. The bridge was designed to resist seismic forces up to a magnitude of 7.0 on the Richter scale. This was achieved through the use of seismic isolation bearings at the base of the piers. These bearings allowed the bridge to move slightly during an earthquake, absorbing some of the energy and reducing the forces transmitted to the structure above. The bridge is also designed to withstand wind speeds of up to 125 miles per hour. The cable-stay design helps to reduce the effects of wind on the structure by distributing the loads across multiple points.
Besides bridges, China also invests a lot of capital into water management. To really put this into perspective, let's take a look at the South-North Water Transfer Project. Launched in response to the acute water shortages faced by the northern provinces, including the densely populated and economically pivotal Beijing-Tianjin region. This mega-project aims to divert water from the Yangtze River in the south to the parched north through a series of canals, tunnels, and advanced pumping stations. Spanning over decades, with its inception dating back to planning stages in the late 20th century, the project is segmented into 3 distinct routes: the eastern route, the central route, and the yet-to-be-completed western route. The central and eastern route collectively form the backbone of this monumental project. Together, they have already transferred billions of cubic meters of water to the northern regions, substantially alleviating water stress in urban and agricultural areas. The financial scale of the South-North Water Transfer Project is staggering, with estimates of the total investment surpassing $80 billion. This figure underscores the complexity and the extensive scope of the project, which involves not only the construction of the physical infrastructure to facilitate the water transfer, but also significant environmental management measures to mitigate the impact on the ecosystems of both the source and recipient areas. The project features state-of-the-art tunneling techniques for crossing under major rivers and traversing diverse terrains, including mountains and urban areas. For example, the project utilizes some of the longest water conveyance tunnels in the world, with advanced boring machines to ensure minimal disruption to the surface. Additionally, it incorporates large-scale pumping stations, equipped with high-capacity pumps, to lift water across significant elevations along the routes. High-performance concrete, resistant to the erosive effects of fast-moving water, ensures the longevity of canals and tunnels. Furthermore, the project's design incorporates extensive measures for water purification and quality control, ensuring that the transferred water meets the stringent standards required for drinking and irrigation. However, the South-North Water Transfer Project is not without its challenges and controversies. The construction of the project's routes and reservoirs has necessitated the relocation of hundreds of thousands of people from their ancestral homes to make way for the infrastructure. Let's move over to Singapore next to investigate the Changi Airport East Development Project. This endeavor is a multi-billion-dollar expansion that will span over 1080 hectares, equivalent to over 1,500 football fields. At its heart is the construction of Terminal 5, a colossal facility that aims to accommodate over 50 million passengers annually, nearly doubling Changi's current capacity. The terminal itself will cover more than 50 hectares, incorporating state-of-the-art technologies and modular design concepts to adapt to changing travel trends. But Terminal 5 is just one aspect of this mega expansion. The project also includes building a third runway, new taxiways, and a vast network of supporting infrastructure. The new runway will stretch over 4 kilometers, ensuring it can handle the largest aircraft in operation. By connecting it to the existing runways and taxiways, Changi will be able to optimize air traffic and manage a substantial increase in flight movements. To deliver this massive undertaking, a workforce of more than 50,000 professionals is engaged across engineering and construction disciplines. Due to limited land availability, innovative reclamation techniques are used, with more than 1,000 hectares of land reclaimed from the sea. Engineers also implement advanced soil consolidation to stabilize the reclaimed land, creating a solid foundation for Terminal 5 and its surrounding infrastructure. The East Development Project will help ease traffic congestion, enabling the airport to serve a projected 135 million passengers annually when complete. Construction began in 2019 and will take over a decade to complete due to the project's scale and complexity. In parallel, Terminal 5 will feature an adaptable design, incorporating modular gates and flexible seating arrangements to accommodate different aircraft types and shifting travel patterns. Compared to other global airport expansions, the East Development Project is unparalleled. For instance, London's Heathrow has similar plans to expand capacity, yet it's only a fraction of Changi's overall growth. The focus on scalability, passenger experience, and operational efficiency will enable Changi Airport to remain resilient in the face of changing travel demands. Let's embark on a journey to Norway to uncover the Nordvegen project. Spanning over 13 miles, this monumental endeavor weaves together a series of tunnels, bridges, and causeways that traverse some of the most challenging terrain in the region. The project commenced in 2017, driven by the need to enhance connectivity and improve the lives of the island residents. At its heart lies the construction of 5 tunnels, the longest of which stretches for nearly 4 miles beneath the seabed. Complementing these tunnels are several grand bridges, including the iconic Lusail Bridge, which arches gracefully over the treacherous waters below. Each bridge is designed not only to withstand the harsh maritime climate, but also to blend seamlessly with the stunning natural surroundings, reflecting a harmonious balance between human achievement. The scale of Nordvegen is underscored by its substantial financial commitment, with costs estimated at around $590 million. This investment reflects the project's importance to the region, promising significant economic and social benefits. Once completed, the road will drastically reduce travel times, transforming what was once a multi-hour ferry journey into a seamless drive of mere minutes. Building Nordvegen presented formidable challenges. The construction teams had to contend with the relentless forces of nature, including unpredictable weather and the powerful currents of the Norwegian Sea. The project's impact extends far beyond mere connectivity. It is set to revitalize the local economy, providing easier access for businesses and boosting tourism. The improved infrastructure will attract new opportunities and investments, fostering growth and development in these previously isolated communities. Now it's time for a different type of underwater project, and for that we have to travel to the United States, where the Lake Mead Intake No. 3 tackles the critical issue of water scarcity. This monumental project, costing an impressive $817 million, was driven by the urgent need to secure a reliable water supply for Las Vegas, a city that depends heavily on the waters of Lake Mead. Initiated in 2008 and completed in 2015, the project involved drilling a 3-mile-long tunnel beneath Lake Mead, one of the largest man-made lakes in the United States. This was no ordinary task. It required the use of a 1,500-ton tunnel boring machine, cutting through the earth at depths reaching 600 feet below the lake's surface. The purpose? To construct a new intake capable of drawing water from the lake's depths, ensuring access to clean water even as lake levels fluctuated perilously low due to prolonged drought conditions. The construction of Intake No. 3 was not just about securing a water source, it was about innovating for the future. Engineers and workers faced the daunting challenge of working in an environment where temperatures soared, and the risk of flooding within the tunnel was a constant threat. Let's
move over to Nevada for the Tesla Gigafactory. With an estimated cost of $16 billion, this massive facility is revolutionizing battery production and energy storage. Gigafactory Tesla is one of the highest volume plants in the world for electric motors, energy storage products, vehicle powertrains, and batteries. Located near Reno, Nevada, the Gigafactory spans 5.3 million square feet, making it one of the largest buildings in the world by footprint. When fully completed, it will cover over 13 million square feet and produce enough batteries to power 500,000 electric vehicles annually. The Gigafactory produces lithium-ion batteries for Tesla electric vehicles and Powerwall energy storage systems. By manufacturing batteries in-house, Tesla reduces costs, increases efficiency, and ensures a stable supply chain. The factory operates on renewable energy, with plans to achieve 100% sustainability. Solar panels cover the roof, and the surrounding area is designed for wind and geothermal energy generation. These efforts align with the mission of Tesla to transition the world to sustainable energy. The Gigafactory has created thousands of jobs in Nevada and attracted additional businesses to the region, boosting the local economy. The expansion is expected to add about 6,500 full-time employees and 4 million square feet of manufacturing space. It has also positioned the US as a leader in battery production and electric vehicle innovation. Despite its achievements, the Gigafactory has faced challenges, including construction delays and supply chain disruptions. Some critics question whether Tesla can meet its ambitious production targets.
The Zun Tower, also known as the CITIC Tower, is a super tall skyscraper located in the heart of Beijing's central business district. The building reaches an astonishing height of 1,732 feet, making it the tallest building in the city and a defining feature of the Beijing skyline. The structure's design was inspired by an ancient Chinese ceremonial vessel known as a zun, which has a broad base, a narrow waist, and a wider top. This unique form required innovative engineering solutions to ensure structural stability. The tower's base is 256 feet wide, narrowing to 177 feet at its thinnest section, then flaring out again to 226 feet at the top. While the shape gives the building its iconic appearance, it's posed significant challenges related to wind loads and seismic forces, both of which are critical factors in high-rise construction. The primary structural system employed in the Zun Tower is a mega frame and core system. This combination allows the building to remain flexible yet stable in the face of lateral forces such as wind and earthquakes. The mega frame consists of enormous steel columns located at the perimeter of the building, which rise through its full height. These columns are connected horizontally by large steel beams that form a grid-like structure. The foundation itself is composed of bored piles driven deep into the ground. Some of these piles extend more than 100 feet below the surface, reaching solid rock layers to provide a stable base for the massive structure. The use of high-strength reinforced concrete in these piles was crucial to ensuring that they could support both the vertical loads from the building's weight and the lateral forces from the wind and earthquakes. In terms of vertical transportation, the Zun Tower features some of the fastest elevators in the world, with a top speed of 33 feet per second. The building's 108 floors are divided into different zones, each served by its own dedicated set of double-decker elevators. This arrangement minimizes the time spent traveling between floors and ensures that the building can handle the thousands of people who work in or visit it daily. To further enhance efficiency, the elevators are connected to a smart dispatch system that groups passengers traveling to the same floors, reducing wait times. The building's facade is another significant engineering feat. Clad in low reflectivity glass and aluminum panels, the facade was designed to reduce solar heat gain while maximizing natural light. This approach reduces the building's reliance on air conditioning, contributing to its energy efficiency. Another crucial aspect of the tower's construction was the tuned mass damper, which is located near the top of the building. This device is a massive weight suspended within the structure, designed to counteract the building's natural sway caused by wind forces. As the wind pushes against the tower, the damper moves in the opposite direction, reducing vibrations and making the building more stable. Without this damper, the occupants on the upper floors would feel an uncomfortable sway during high winds, and the building itself could suffer from structural fatigue over time. The construction of the Zun Tower was a logistical challenge due to the density of Beijing's central business district. Given the limited space, much of the building's components, such as steel columns and beams, were prefabricated off-site and transported to the construction site for assembly. This method minimized disruption in the area and allowed the construction to proceed quickly and efficiently. Large tower cranes, some reaching heights of more than 1,600 feet, were used to hoist the prefabricated sections into place. These cranes operated in conjunction with GPS systems to ensure the precise alignment of each component. The tower also connects to a vast underground network that includes parking spaces, retail shops, and access to Beijing's subway system. The underground portion of the building extends to a depth of 98 feet, supported by a raft foundation that distributes the weight of the structure across a large area. This foundation also helps to resist the upward pressure from groundwater, which can cause buildings to shift or settle unevenly.
The next Chinese megaproject is truly stunning, being among the highest bridges in China. I'm talking about the Pingtang Bridge, positioned in the rugged terrain of Guizhou Province. Completed in December 2019, this bridge is pivotal for local development, reducing travel times and linking communities previously separated by challenging terrain. The bridge's design incorporates a hybrid approach, melding elements of both cable-stayed and suspension bridge technologies. This innovative strategy was chosen to address the unique challenges posed by the site, including high winds and the need for a long span without intermediate supports. The design features 3 main pylons, with the tallest standing at an impressive height of 332 meters. These pylons support the bridge deck with a series of stay cables, which are crucial for maintaining the structure's stability and distributing loads evenly. With a main span of 1092 meters and a total length of 2135 meters, the Pingtang Bridge is among the world's longest span bridges. It hangs approximately 332 meters above a river, making it one of the highest bridges globally. This engineering feat required a budget of approximately 1.5 billion yuan, or $215 million, reflecting the complexity and scale of the construction effort. Construction of the Pingtang Bridge was a logistical and engineering challenge. The remote location and difficult terrain necessitated innovative solutions for transportation and assembly of large structural components. The Chinese project team placed a strong emphasis on environmental conservation, implementing measures to minimize the bridge's impact on the surrounding ecosystem. Strategies included careful routing of the bridge to avoid ecologically sensitive areas, erosion control measures to protect the local watershed, and efforts to preserve the natural landscape. But we have to travel to China next for a massive airport project. Enter Beijing Daxing International Airport, an architectural marvel that rises from the plains of Daxing District, just 46 kilometers south of Tiananmen Square. Nicknamed the Starfish, this engineering feat spans over 47 square kilometers, making it the largest single-structure airport terminal in the world. Inaugurated in 2019, it was envisioned to alleviate pressure from Beijing Capital International Airport, meeting the needs of China's bustling capital while positioning Beijing as a global aviation powerhouse. Designed by the renowned architect Zaha Hadid in collaboration with Chinese partners, the airport is a blend of futuristic aesthetics and functional efficiency. Its iconic starfish-shaped terminal radiates out into 6 curved arms that bring all departure gates within an 8-minute walk from the security checkpoint. With a budget of nearly $17.5 billion, construction began in 2014. The roof alone stretches over 1,800 square meters, about the size of 25 soccer fields. To manage the tremendous influx of travelers, Daxing features 4 runways capable of handling the largest aircrafts and more than 100 aircraft stands. The airport's advanced baggage handling system can process up to 3,000 bags per hour, while artificial intelligence optimizes passenger flows and reduces wait times. The energy efficiency of the terminal is also remarkable, with a ground source heat pump system and over 2.5 million square feet of solar panels on site. Such sustainable practices help reduce the airport's carbon footprint, aligning with global environmental goals. Daxing Airport was planned not only as an aviation hub, but as a new economic center. Connected by high-speed rail and expressways, it's a 20-minute train ride from downtown Beijing. By 2040, the airport aims to handle up to 100 million passengers and 4 million tons of cargo annually. Despite its incredible achievements, construction faced challenges due to the swampy terrain, requiring engineers to implement deep foundation piles and water control measures to stabilize the ground. Complex airspace coordination was also crucial, as Daxing operates near Beijing's existing airport. But what about the Puente de Rande project, located in Spain? This iconic bridge, integral to the region's infrastructure, not only facilitates efficient transportation, but also stands as a symbol of modern engineering. Constructed in 1978 and expanded significantly in recent years, the Puente de Rande connects the city of Vigo with the Marazzo Peninsula, playing a critical role in the AP9 highway. The original bridge was designed by Italian engineer Fabrizio de Miranda, known for his expertise in long-span bridges. It stretches over 1.1 miles, making it one of the longest bridges in Spain. The expansion project, initiated in 2015 and completed in 2018, was driven by the need to alleviate traffic congestion and improve safety. The upgrade involved the addition of 2 new lanes, increasing the bridge's capacity to 6 lanes. This expansion was a challenging engineering feat, requiring precise planning and execution to ensure the bridge remained operational throughout the construction process. The project cost approximately $191 million, reflecting the complexity and scale of the undertaking. One of the standout features of the expansion was the use of innovative construction techniques, such as the installation of new decks alongside the existing structure without closing the bridge to traffic. This approach minimized disruption and showcased the ingenuity of modern bridge engineering. The Puente de Rande serves as a vital link for the region's economy. By improving the connectivity between Vigo, one of Spain's busiest ports, and the surrounding areas, the bridge supports local industries, including shipbuilding, fishing, and tourism. While the next underwater project may not be as big, the Poseidon Underwater Hotel is just as remarkable. This groundbreaking project, aiming to be nestled in the clear turquoise waters of Fiji, extends the frontier of hospitality into the aquatic realm. The hotel is designed to feature 25 suites, each encased in a 70mm thick transparent acrylic shell, providing 360-degree views of the vibrant marine ecosystem. With an estimated construction cost of $105 million, the hotel's ambition is not just to provide luxury, but to pioneer in eco-friendly engineering. The structure is planned to be anchored at a depth of 40 meters below the sea level, covering an area of approximately 5,000 square meters.
The Kong-Zhuhai-Macau Bridge is the longest sea-crossing bridge in the world, spanning 34 miles and connecting the three cities of Hong Kong, Zhuhai, and Macau. This mega infrastructure project required nearly a decade to complete, with a final cost of approximately $18.8 billion. The bridge's construction involves several critical engineering and construction challenges, particularly due to the geological and environmental conditions of the Pearl River Delta. The foundation of the bridge was one of the most complex aspects due to the region's soft seabed and strong tidal flows. Engineers need to install pile foundations deep into the seabed to stabilize the bridge pylons. In some areas, piles were driven up to 377 feet into the ground, ensuring that the foundation would withstand the weight of the superstructure, as well as the constant motion of water and weather conditions. The piles were reinforced with steel and concrete, which provided the necessary strength and corrosion resistance, critical in marine environments. The bridge is composed of several different structural components, including long stretches of viaducts, 3 cable-stayed bridges, and a tunnel. The cable-stayed bridges were needed to provide enough clearance for shipping lanes, with the longest main span measuring 1,588 feet. Each bridge tower, which supports the cables, rises several hundred feet above the water and required precise construction to handle the high wind loads typical in the region. One of the most innovative aspects of the bridge is the submerged tunnel, which spans 4 miles beneath the Lingding Channel. The tunnel was built using the immersed tube method, where large sections of the tunnel were prefabricated on shore and then floated to the construction site. Once in position, these massive tube sections, each weighing 80,000 tons, were sunk into a pre-dredged trench on the seabed. Divers and automated systems guided the placement of each section, ensuring a watertight fit. The sections were connected by rubber gaskets and sealed with concrete, forming a continuous underwater tunnel. To keep the tunnel from shifting or floating due to buoyant forces, it was anchored to the seabed using heavy concrete ballast blocks. The construction of the tunnel also required the creation of 2 artificial islands. These islands, measuring 0.6 square miles each, were built to house the entrances and exits of the submerged tunnels, as well as to provide ventilation and emergency access points. Engineers used a combination of land reclamation techniques and specialized retaining walls to build these islands in the open sea. The process involved the placement of millions of cubic yards of sand and rock to form a stable base, followed by the installation of retaining walls to prevent erosion. The artificial islands and bridge pylons were constructed using prefabrication techniques, which allowed large sections to be built off-site and then transported to the construction area. This method sped up the construction process significantly and reduced the risk of errors, as prefabricated components were created in controlled environments, ensuring consistency in materials and workmanship. The bridge also required extensive drainage and water management systems. Since the bridge spans open water, rainwater and tidal water could easily accumulate on the bridge deck. To mitigate this, engineers designed a drainage system that uses gravity-based systems to channel water off the bridge deck and into collection systems at regular intervals. These collection points direct the water into pipes that run along the bridge and release it back into the sea in a controlled manner, preventing flooding and ensuring safe driving conditions. In addition to its complex structural design, the bridge also features several intelligent monitoring systems. These systems include sensors embedded in the bridge deck and towers to monitor strain, displacement, and vibrations in real time. The data collected from these sensors is continuously analyzed to detect potential issues before they become critical, allowing for preventative maintenance and ensuring the long-term safety and reliability of the bridge. The project was designed to have a lifespan of 120 years, a figure made possible by the use of high-quality materials, advanced corrosion-resistant coatings, and regular maintenance protocols. The steel and concrete components of the bridge are coated with anti-corrosion paints and other protective materials to resist the effects of saltwater, wind, and humidity. Maintenance access points were built into the bridge's design, allowing for regular inspections and repairs without disrupting traffic flows.
It's time to travel to Pudong International Airport, which serves as a crucial hub in East Asia. Officially opened on October 1, 1999, this airport not only serves as a vital artery for international travel, but also stands as a symbol of modern engineering. With its strategic location in Pudong, Shanghai, it's designed to manage the demands of heavy passenger and cargo traffic, contributing significantly to the region's economic development. The airport's construction was a monumental project with an initial investment of approximately $1.67 billion for its first phase. This phase included the main terminal, a runway, and supporting transportation infrastructure, setting the stage for what would become one of the busiest airports in the world. The airport has since undergone several expansions, including the addition of Terminal 2 in 2008 and Terminal S1 for Spring Airlines in 2019, pushing its capacity and facilities to meet the growing demands of international travel and cargo services. Covering an area of over 25 square miles, the airport features 5 total runways, with the latest opening in 2020, where it only had 2 runways before. This expansion was critical to accommodate the airport's increasing traffic, which saw over 76 million passengers in 2019, making it one of the top 10 busiest airports globally by passenger traffic. The terminal buildings are notable for their modern design, incorporating energy-efficient materials and systems. Advanced baggage handling systems, automated check-in kiosks, and facial recognition technology for security screenings exemplify the integration of technology to enhance operational efficiency and passenger experience. However, the airport's expansion has not been without challenges. The construction phases witnessed logistical challenges, including the coordination of a vast workforce and the seamless integration of new terminals and runways into the existing infrastructure without disrupting airport operations. These problems highlighted the complexities of executing large-scale infrastructure projects in a bustling urban setting. It's time to travel to the coast of Kuwait, where the Al-Zour refinery is located. This enormous oil refinery is one of the largest of its kind, with a capacity to process 615,000 barrels per day, fueling not just Kuwait's energy ambitions but also global markets. The sprawling site covers over 14 square kilometers, making it comparable to 19 football fields in size. The Al-Zour refinery, with an estimated cost of over $16 billion, was conceived to refine Kuwait's heavy crude oil and produce low-sulfur fuel oil that will meet international emission standards. The facility is not only impressive in its size, but also in its engineering, which has required innovative construction methods to build the 6 main refining units that house some of the world's largest processing equipment. Construction began in 2015, and by 2022 the refinery started its first phase of operations. The plant's advanced technology enables it to produce ultra-low sulfur diesel, kerosene, and naphtha. This not only bolsters Kuwait's refining capabilities, but also addresses international demands for cleaner fuel alternatives. The Al-Zour refinery is part of Kuwait's broader Clean Fuels project, which aims to overhaul its energy sector by providing environmentally friendly fuel. But constructing this colossal project wasn't without its challenges. The desert terrain posed difficulties in laying out the vast network of pipes and electrical infrastructure. The logistics of transporting enormous equipment to the remote site required careful planning, as some components like the distillation columns and reactors weighed over 500 tons each. To tackle this, a purpose-built port was established nearby to accommodate large cargo ships. The refinery employs a sophisticated control system that integrates automation and data analytics, providing real-time monitoring of every stage of the refining process.
The Shantou Bay Tunnel is one of the most complex engineering projects in China. As part of the Shantou Railway, this sub-sea tunnel is a significant component that enhances the transportation network in the region. The tunnel runs 30,150 feet in total length, with 7,118 feet of that length passing under Shantou Bay. It is specifically designed for high-speed rail, allowing trains to travel up to 217 miles per hour. The subsea section of the tunnel was constructed using a shield tunneling method, one of the most advanced techniques in tunnel construction. The tunnel boring machine used for the Shantou Bay Tunnel, named Yongping, has an excavation diameter of 47.8 feet. This TBM had to penetrate through complex geological strata, which included hard rock formations, boulders up to 16 feet in diameter, and soft marine sediments. The TBM was specially designed for this project and equipped with a mud-water balance system to maintain tunnel stability while managing water pressure from the bay above. This balance system allows the shield to move forward steadily while preventing groundwater from leaking into the tunnel. The TBM had a cutter head that could withstand significant forces, given the maximum rock strength encountered during tunneling was measured at 24,000 psi. The machine also included specialized tools for changing the cutting tools under normal atmospheric pressure, which reduced downtime and increased operational efficiency. The logistics of maintaining the TBM involved routine inspection and replacement of parts while it was deep underground, a feat that required innovative approaches to ensure safety and efficiency. Given the tunnel's subsea location, the maximum burial depth reached 220 feet below sea level. Engineers had to consider not only the weight of the water above, but also tidal forces and the shifting nature of the seabed. Extensive geotechnical surveys were conducted before construction to understand these forces better and to design a tunnel that could withstand them. The tunnel was designed with a double-layer lining system, with the outer lining providing structural strength and the inner lining acting as a waterproof barrier. One of the most difficult engineering challenges came from dismantling the large-diameter TBM after it completed its section of the tunnel. The TBM was too large to be removed in one piece, so it had to be disassembled within the tunnel. The operation required lifting some components that weighed up to 220 tons. Specialized cranes and transport systems were used to carefully extract these heavy components through the tunnel without damaging the already constructed sections. Construction logistics also played a significant role in the success of the project. Given the tight construction timeline, materials such as steel tunnel segments were prefabricated off-site and brought to the construction site by barge. This approach minimized delays and allowed for precision manufacturing in controlled environments. Once the segments arrived, they were transported into the tunnel by rail-mounted systems, then lifted into place by hydraulic arms attached to the TBM. In addition to its structural challenges, the Shantou Bay Tunnel was designed to handle high-speed rail traffic, a unique requirement that added complexity to the project. To ensure the tunnel could accommodate trains traveling at speeds up to 217 miles per hour, engineers had to create a perfectly smooth track system within the tunnel. This was achieved by laying continuously welded rail, which eliminates the gaps between traditional rail sections and reduces the vibrations caused by high-speed trains.
China is also exceptional at building high into the sky, and that's why we're taking a look at the Shanghai Tower. Rising majestically above the Lujiazui skyline, the Shanghai Tower was conceived with the dual purpose of symbolizing Shanghai's global financial prominence and pioneering sustainable urban living concepts. With its completion in 2015, the tower not only achieved its aim of being a financial center, but also became a model for future eco-friendly skyscrapers. The project, which began construction in November 2008, faced a lengthy development phase before reaching its completion 7 years later, reflecting the complex nature of constructing one of the world's tallest buildings. Costing approximately $2.4 billion, the Shanghai Tower stands as a financial behemoth, indicative of the massive investment in creating a landmark that merges architectural innovation with environmental stewardship. Spanning an area of 380,000 square meters, this 632-meter-tall skyscraper is not only a marvel of height, but also of space and design, featuring the world's second fastest elevators, which ascend at a speed of 18 meters per second. The construction of the Shanghai Tower introduced several innovative techniques and materials to address the unique challenges posed by its design and environmental goals. One of the most notable is its double-skin facade, designed to insulate the building and reduce the need for heating and cooling, thereby significantly cutting energy costs. This outer layer wraps around the building, creating a buffer zone that acts as thermal insulation, a feature that is critical in Shanghai's variable climate. However, like many other megaprojects, the Shanghai Tower faced unique challenges during construction. Building such a massive structure in the densely populated area of Lujiazui posed potential problems, including traffic congestion and strain on local resources. Moreover, the financial viability of the project was questioned, with skeptics pointing to the high vacancy rates of office spaces in Shanghai and wondering whether the tower would become a vertical ghost town. As of 2019, 55 out of 128 floors sit empty, which is close to 50%. Another point of contention was the engineering challenge of constructing a skyscraper of such unprecedented height and complexity. The Shanghai Tower employs a unique twisting form designed to reduce wind loads on the building by 24%.
The Three Gorges Dam, located in the Yangtze River in Hubei Province, is the largest hydroelectric dam in the world in terms of both installed capacity and concrete volume. The project began in 1994, with the main construction phase spanning 17 years, and it was fully operational by 2012. The dam is 7,660 feet long and stands 607 feet tall, with a total reservoir capacity of 5 trillion gallons of water. The dam's power station consists of 32 main turbines, each with a generating capacity of 700 megawatts, and 2 smaller turbines at 50 megawatts each, bringing the total generating capacity to 22.5 gigawatts. The sheer scale of the project required monumental efforts in planning, engineering, and construction. One of the primary engineering challenges was managing the Yangtze River's flow, which ranks among the largest rivers in the world. Before construction could even begin, engineers needed to build a diversion channel that could temporarily reroute the river's flow while the dam's foundations and key structures were being built. This channel was completed in 2002 and allowed the river to continue flowing while major sections of the dam were under construction. The dam spillway was another significant engineering challenge. During heavy rain or when the reservoir reaches capacity, excess water needs to be discharged in a controlled manner to prevent the dam from overtopping or failing. The Three Gorges Dam is equipped with 23 floodgates, each of which can release up to 3 million cubic feet of water per second. The spillway system was designed to handle a 1 in 10,000 year flood, meaning it can manage an extreme flood event that statistically only occurs once in 10,000 years. These floodgates were built using high-strength steel and advanced hydraulic systems to ensure that they can operate reliably under extreme conditions. The hydroelectric power generator system at Three Gorges Dam is one of the most complex in the world. Each of the dam's turbines weigh over 6,600 tons and measure 33 feet in diameter. The turbines are housed in 2 separate powerhouses located on either side of the dam, and each powerhouse is capable of generating 11 gigawatts of electricity. The powerhouses were constructed using precast concrete segments that were assembled on site. These segments were manufactured to precise specifications to ensure that the massive turbines could fit perfectly into their housings. The turbines themselves are of the Francis type, which are well suited for handling large volumes of water with relatively low head pressure. During the construction of the dam, cofferdams were built to allow workers to build sections of the main dam structure in the dry. These cofferdams, which were constructed from rockfill and reinforced with concrete, were essential for controlling the flow of the river during the construction process. The cofferdams also acted as a safeguard, providing temporary flood protection in case of an unexpected rise in water levels. Once the main sections of the dam were completed, the cofferdams were gradually removed, and the river was allowed to flow through the dam's newly installed turbines. The lock system at the Three Gorges Dam is another important aspect of the project, allowing ships to pass through the dam and continue their journey along the Yangtze River. The dam's lock system consists of 5 stages, with each lock measuring 918 feet in length and 114 feet in width. The system is designed to accommodate vessels up to 10,000 tons, and it allows ships to overcome the 370-foot difference in water level between the downstream and upstream sides of the dam. The locks were constructed using reinforced concrete and equipped with state-of-the-art hydraulic systems that control the water levels in each chamber. An important aspect of the dam's construction was ensuring that the dam and the reservoir could withstand the immense hydraulic pressure generated by the weight of the water. To manage this, engineers incorporated buttress supports into the upstream side of the dam. These supports act as braces that distribute the force of the water evenly across the dam structure, reducing the risk of localized stress points that could lead to structural failure. The buttresses were constructed using high-strength concrete that was specifically designed to withstand prolonged exposure to water without deteriorating. The Three Gorges Dam Reservoir covers an area of 400 square miles and stretches more than 370 miles upstream. The reservoir not only serves as a source of hydroelectric power, but also provides flood control for the lower reaches of the Yangtze River.
For the next Asian megaproject, we have to travel to Japan. This is where the Chuo Shinkansen project is located, a maglev marvel that links Tokyo to Nagoya at mind-boggling speeds of up to 500 kilometers per hour. This high-speed rail megaproject aims to revolutionize inner-city transport, slicing travel time between the two cities from 100 to a mere 40 minutes. The Chuo Shinkansen is poised to become the world's fastest land transportation system, delivering passengers across 286 kilometers with unparalleled efficiency. The engineering genius behind this project lies in the magnetic levitation technology, which eliminates the friction of traditional rail systems by suspending the train in midair using powerful superconducting magnets. This innovative approach, which has been in development since the 70s, propels the train forward smoothly and quietly. But the path from concept to completion has been anything but straightforward. The construction process requires massive excavation work, as over 85% of the line will be underground or within tunnels, including the longest rail tunnel in Japan, stretching a remarkable 25 kilometers. The entire project has an estimated price tag of $50 billion for the Tokyo-Nagoya stretch alone, making it one of the costliest rail projects ever conceived. Over 15,000 workers are on site daily, boring through some of Japan's most challenging terrain, including the Central Alps. When fully operational, the Chuo Shinkansen will accommodate up to 1,000 passengers per train, potentially transporting over 80 million passengers annually. It will also expand to reach Osaka in the project's second phase, providing an alternative to both air and road travel. In comparison to other global rail projects, the Chuo Shinkansen stands in a class of its own. Its technological ambition far surpasses high-speed lines in Europe or the United States, while its environmental considerations make it a template for future high-speed rail developments. Let's move to the next impressive Chinese megaproject, called the Chongqing-Kunming High-Speed Railway. This pivotal project, stretching over 720 kilometers or 447 miles, connects two major cities in southwest China, Chongqing and Kunming. The railway, part of China's grand plan to create a 30,000-kilometer high-speed rail network, underscores the nation's ambition to lead globally in rail technology and infrastructure. Costing approximately 100 billion yuan or $15 billion, the Chongqing-Kunming high-speed railway is not just an economic investment but a technological showcase. It traverses some of China's most challenging terrains, including mountains, valleys, and rivers, necessitating innovative construction methods and technologies. The project features numerous tunnels and bridges, including the world-renowned Wulong Mountain Super Bridge. The railway reduces the travel time between Chongqing and Kunming from over 20 hours to just 4.5 hours, significantly impacting the social and economic landscape of the region. It enhances accessibility, promotes tourism, and fosters economic integration between the southwestern provinces. The construction of this railway employed cutting-edge machinery and materials with a focus on durability and safety. High-strength steel, advanced concrete composites, and state-of-the-art track-laying techniques were utilized, ensuring that the railway could withstand the region's seismic activity and extreme weather conditions. The use of tunnel boring machines and bridge-building gantries played a pivotal role in accelerating the construction pace, demonstrating China's prowess in leveraging technology for infrastructure development. One of the key challenges encountered during the construction was the environmental impact, particularly in ecologically sensitive areas. The project team implemented several mitigation strategies, such as rerouting sections of the track, constructing wildlife crossings over and under the railway, and implementing strict construction practices to minimize the disturbance to the natural landscape. But the project has not been without its controversies, including concerns over land acquisition and environmental degradation. The government and project developers have faced criticism over the lack of transparency and adequate compensation for those affected. Despite these challenges, the Chongqing-Kunming high-speed railway remains a symbol of progress and a critical component of China's vision for a modern country.
The Hongian Bridge in Guangzhou, China, is a significant piece of infrastructure that demonstrates cutting-edge engineering and construction techniques. It stretches over 5,800 feet and is located in the Nansha Free Trade Zone, part of the Guangdong-Hong Kong-Macau Greater Bay Area. This cable-stayed bridge spans the Longzhuai South Waterway and was constructed to carry not only vehicular traffic but also high-voltage cables, gas pipelines, communication systems, and water pipelines, making it a multifunctional structure. The design and construction of the Hongian Bridge reflects some of the most advanced methods currently used in bridge-building projects worldwide. A key feature of the Hongian Bridge is its cable-stayed design, which utilizes a double tower and double cable plane configuration. This design was chosen due to the need to support the large span of the main bridge, which measures 1,900 feet. The main towers, which are essential to the stability of the structure, rise to heights of 590 feet. These towers are designed in an H shape, which provides structural strength and aesthetic appeal. Constructing such massive towers required a high degree of precision, particularly given the complex geological conditions of the region. The foundations of the towers had to be extremely robust to handle both the weight of the bridge and the environmental forces acting on it, such as wind, waves, and tidal shifts. The geological conditions of the Pearl River Delta posed a significant challenge. Engineers had to work with a foundation of soft soils which required extensive reinforcement. Deep foundation piles, measuring over 100 feet in length, were driven into the seabed to provide stability for the main towers. These piles were reinforced with steel to ensure that they could bear the immense loads placed on them by the structure above. Moreover, the construction had to be coordinated around the flow of shipping traffic in the region, as the bridge is located near a heavily trafficked waterway. Another critical aspect of the Hongian Bridge's construction was the use of steel box girders for the bridge deck. These girders, which span 1,900 feet between the towers, were prefabricated off-site to minimize the amount of work needed in the challenging marine environment. Once fabricated, the steel box girders were transported to the site and lifted into place using massive floating cranes, capable of handling loads of up to 600 tons. These girders were connected using high tensile bolts and welding techniques to create a continuous deck that is both strong and flexible, allowing the bridge to absorb the forces generated by wind, traffic, and seismic activity. The installation of the stay cables, which connect the bridge deck to the towers, was another challenging phase of construction. A total of 144 stay cables were installed, each of which had to be carefully tensioned to ensure that the forces acting on the bridge were distributed evenly. These cables range in length, with the longest measuring over 1,000 feet and weighing more than 23 tons. Specialized equipment, including tower cranes and winches, was used to lift the cables into place and tension them to the precise specifications required for the bridge's design. In addition to the bridge's structural elements, the construction process itself was a logistical challenge. Given the size of the components involved and the complexity of working in a marine environment, the project required the coordination of multiple cranes, barges, and other heavy equipment. The steel box girders were prefabricated in sections and transported to the construction site by barge. Once on site, they were lifted into place by cranes operating from floating platforms and precisely positioned using GPS technology to ensure that the alignment met the design specifications. One unique feature of the Hongian Bridge is its ability to carry utilities, including high-voltage power cables and gas pipelines. This required engineers to develop specialized techniques for integrating these utilities into the structure without compromising its integrity and safety. The cables and pipelines are housed in dedicated channels within the bridge deck, and access points have been built into the structure to allow for maintenance and inspection without disrupting traffic.
Let's journey to Norway to explore the remarkable Follo Line project. This megaproject is an essential part of the inner-city triangle, which aims to improve transportation efficiency across the eastern part of Norway. The project began construction in 2015 and opened up to the public in 2022. This new railway line stretches over 22 kilometers and includes the longest railway tunnel in Scandinavia, measuring 19 kilometers. The entire project comes with a hefty price tag of around $2.4 billion, reflecting its vast scale and the cutting-edge technology employed. One of the most ambitious aspects of the Follo Line is its twin tunnel system. Bored through solid rock, these parallel tunnels will drastically reduce travel time between Oslo and Ski, cutting it down to just 11 minutes from the previous 22. The construction of these tunnels involved the use of 4 state-of-the-art tunnel boring machines, each named after historical Norwegian women. These colossal machines, each over 150 meters long, worked simultaneously to excavate the tunnels. A notable engineering challenge of the Follo Line project was the need to navigate through complex geological conditions, including hard gneiss rock and sections of softer ground. Advanced ground freezing techniques were employed in some areas to stabilize the ground, ensuring the safety and stability of the tunnels during excavation. In addition to the tunnels, the Follo Line includes the construction of new stations and upgrades to existing infrastructure. The new ski station is designed to handle increased passenger volumes and will feature modern amenities, including expanded platforms and improved accessibility. These upgrades are expected to accommodate the projected rise in passenger numbers, making train travel more convenient and attractive. It's time to move on to one of the biggest pipeline megaprojects in the world, called the Nord Stream gas pipeline. Stretching beneath the Baltic Sea to connect Russia with Germany, this strategic pipeline, operational since November 2011, spans approximately 124 kilometers, making it one of the longest offshore gas pipelines in the world. With a total project cost estimated at 8.8 billion euros, the Nord Stream has the capacity to transport up to 55 billion cubic meters of natural gas annually, playing a crucial role in ensuring energy security and diversification of supply routes in Europe. Constructed using state-of-the-art technology, the pipeline comprises 2 parallel lines, each made from tens of thousands of steel pipes welded together on board specialized vessels. These pipes, coated for corrosion resistance, were laid on the seabed by some of the world's most advanced laying ships, navigating through challenging marine conditions. Despite its technical achievements, Nord Stream has been mired in controversy. Critics argue that it increases European dependency on Russian gas, posing geopolitical risks. Environmental groups have also raised concerns about the potential impacts on the Baltic Sea's delicate ecosystem. Yet, proponents highlight its contribution to energy security and lower carbon emissions compared to coal and oil.
The Xiang'an Railway Station is one of the most ambitious infrastructure projects in China, designed to serve as a key transportation hub within the Xiang'an area. Covering over 5.1 million square feet, this massive project required the implementation of advanced construction methods and cutting-edge engineering. The station connects high-speed rail lines from Beijing, Tianjin, and other cities across China, making it a cornerstone of the regional transportation network. The project costs about $1.13 billion and plays a pivotal role in China's vision for the coordinated development of the Beijing-Tianjin Hebei region. One of the main challenges of the construction was the integration of the station with surrounding infrastructure and transport systems. To manage this, engineers used building information modeling throughout the planning and construction phases. The digital modeling technology allowed project managers and engineers to visualize every aspect of the station's construction in 3 dimensions, helping them to foresee potential conflicts between structural elements and utilities. By modeling the station digitally, the planners were able to anticipate and resolve issues related to the integration of train lines, roadways, and urban utilities long before construction began. The station consists of 5 floors, 3 of which are above ground and 2 underground. The underground floors contain the platforms for the high-speed trains that connect Xiang'an to Beijing and other major cities. Above-ground floors house the station's entrances, ticketing services, and waiting areas, all of which were designed to manage massive passenger flows. The station's structural framework is supported by a steel-reinforced concrete system. This system combines the compressive strength of concrete with the tensile strength of steel, allowing the station to support the immense loads imposed by its large spans and high ceilings. The main beams and columns were constructed using prefabricated steel components, which were manufactured off-site and then transported to the station. Prefabrication helped to reduce construction time and improve the quality control of the components since they were made in controlled factory environments. The foundation work for the station was particularly complex because of the soft soil conditions in the Zhongin area. Engineers needed to ensure that the station's foundation could support the heavy weight of the building and the rail infrastructure above it. To address this, they used deep foundation piles, some of which extended more than 164 feet into the ground. These piles were designed to distribute the weight of the structure evenly across the foundation and to prevent uneven settlement, which could compromise the station's structural integrity. In areas where the soil was particularly soft, engineers employed advanced techniques like soil stabilization to improve the bearing capacity of the ground. The roof structure of the Zhongin Railway Station was another significant engineering challenge due to its sheer size. The roof covers an area larger than 14 football fields and consists of a network of steel trusses that span large distances without intermediate supports. Engineers opted for a lightweight steel truss system to minimize the weight of the roof while ensuring that it could withstand the high winds and heavy snow loads typical in the region. These steel trusses were pre-assembled on the ground before being lifted into place using massive cranes. This method reduced the amount of time workers spent at dangerous heights and sped up the overall construction process. The construction of Zhongin Railway Station also had to meet rigorous seismic safety standards given the region's susceptibility to earthquakes. To ensure that the station could withstand seismic activity, engineers incorporated base isolators into the foundation. These isolators allow the building to move independently of the ground during an earthquake, absorbing much of the energy generated by seismic waves and preventing damage to the building's superstructure. The station's main support columns were also designed to be more flexible than traditional structures, giving them the ability to sway without cracking or collapsing under extreme forces. In terms of construction materials, engineers used high-strength concrete in critical areas of the station, particularly in the load-bearing columns and beams. This concrete has a compressive strength of over 10,000 psi, making it ideal for supporting the station's massive structural loads. Steel rebar was also used extensively throughout the station to provide tensile reinforcement, prevent cracking, and increase the structure's resistance to bending and shear forces.
China is not only industry-leading in constructing bridges and railways, but also creates stunning new cities. Let's dive into Tianjin Eco-City, which is designed to house approximately 350,000 residents in an area covering about 19 square miles. The project emerged from mutual concerns over rapid urbanization, environmental degradation, and the sustainability of future cities, leading to its initiation in 2008. The financial blueprint of the Tianjin Eco-City is as ambitious as its environmental targets, with investment figures projected to be near $10 billion, aiming to cover infrastructure, residential, and commercial development costs. This funding is directed towards not just constructing buildings, but also towards creating an integrated environment that supports sustainable living practices across energy use, water management, and waste disposal. One of the critical aspects of the Tianjin Eco-City is its emphasis on green building materials and advanced construction technologies. The city employs a variety of eco-friendly materials, including recycled concrete and sustainable timber. Innovative construction methods are utilized to ensure energy efficiency and resource conservation. These include the use of prefabricated parts to reduce construction waste and the implementation of smart technologies for water and energy management, showcasing a comprehensive approach to sustainable urban development. Despite its noble aspirations, skepticism arose over the feasibility of transforming a polluted, saline wasteland into a thriving eco-city. Concerns were also raised regarding the project's scalability and whether it could truly be replicated in other contexts, considering the significant initial investment and the need for technological innovation. The project encountered practical hurdles in attracting residents and businesses, crucial for the city's sustainability. The eco-city's location, distant from Tianjin's urban core, and the premium cost of living posed barriers to rapid population growth. This challenge highlighted the difficulty of balancing environmental goals with economic and social viability, a crucial lesson for future eco-city projects. Despite these obstacles, the Tianjin Eco-City continues to evolve, with ongoing construction and development reflecting both the challenges and potential of sustainable urban living. Let's journey to Vietnam next, where the North-South Railway, a modern reincarnation of the historic Reunification Express line, is Vietnam's most ambitious rail infrastructure project. Stretching over 1,700 kilometers from Hanoi in the north to Ho Chi Minh City in the south, this project aims to modernize and expand Vietnam's railway system. At an estimated cost of $58.7 billion, this megaproject will feature high-speed rail capable of whisking passengers at speeds up to 350 kilometers per hour. Once complete, it will slash travel times between the two cities from over 30 hours to around 6 hours, creating a seamless transit corridor between the economic hubs. The project includes 23 stations and is divided into two primary segments, each built simultaneously. The high-speed rail system will ride on a standard gauge track supported by pre-stressed concrete sleepers and bridges that cross Vietnam's diverse terrain. As much of the line traverses challenging landscapes, extensive tunneling is necessary, particularly in the mountainous central regions. Engineers have already identified the need for over 30 tunnels totaling nearly 50 kilometers. One of the project's central challenges lies in navigating the densely populated areas while minimizing land acquisition issues. Innovative design measures like elevated tracks and noise barriers have been adopted to mitigate disruption. Advanced construction methods, such as incremental launching and cantilever segmental techniques, ensure that bridges and tunnels are built efficiently and safely. Beyond its transformative speed, the North-South Railway will significantly reduce carbon emissions by diverting traffic from roadways. But how about a tunnel that has been connecting two countries for over 2 decades? Let's check out the Øresund Tunnel, which is part of the Øresund Link that connects Denmark and Sweden, facilitating unprecedented connectivity between the two countries since its completion in 2000. This project, with a total cost of around €4 billion for the entire Øresund Link, includes a bridge, an artificial island, and the tunnel itself, showcasing a blend of engineering ingenuity and cooperation across borders. Stretching 4 kilometers beneath the Øresund Strait, the tunnel complements the 8-kilometer bridge to form a comprehensive transport route. The construction of the tunnel employed the cut-and-cover method, where a trench was excavated on the seabed, and prefabricated tunnel sections were then lowered into place. The Øresund Tunnel has significantly reduced travel time between Denmark and Sweden, bolstering economic ties and cultural exchange.
We have to talk about the redevelopment of one of the busiest airports in the country, John F. Kennedy International Airport. This project is worth $19 billion and is all set to redefine air travel for one of the busiest hubs in the United States. With over 62 million passengers passing through annually, JFK is integral to global connectivity. The airport generates more than $51 billion in sales and $17.1 billion in wages. This massive project ensures that the airport not only meets current demands, but is also prepared for future growth. The JFK International Airport Master Plan to redevelop the airport into a world-class 21st century airport is being led by Grimshaw and Mott MacDonald. The expansion will result in new terminal complexes on both the south and north sides of the airport. To the south, Terminals 1 and 2 will be replaced with a new terminal served by 23 international gates. On the north side, another upgraded terminal will connect to the existing Terminal 5 and offer 12 international gates, each able to serve larger wide-body aircraft. Other expansion projects include a 16-gate expansion for Terminal 4 and a 3-gate expansion at Terminal 8. The project also focuses on enhancing the passenger experience through modern design, spacious concourses, advanced technology, and sustainable features. Improvements include better check-in areas, automated security systems, and a wider range of retail and dining options. Upgraded baggage handling systems will streamline operations, reducing delays and improving efficiency. To complement the terminal upgrades, the project includes a redesign of roadways and parking areas to ease congestion and improve traffic flow. Expanded air train capacity will provide a seamless connection to public transportation. Similarly, upgrades to taxiways and aprons ensure better aircraft movement on the ground. With new roads, bridges, and enhanced traffic technologies, travelers will have an easier time navigating between terminals. They are also reducing the number of roadway loops from 5 to 2 main loops, making it less confusing for drivers. This will eventually create space for more cars to circle through, but less congestion to stack up. This includes a multi-level parking facility with nearly 2,000 spaces and an eco-friendly timber exterior. A 122-meter pedestrian bridge equipped with rainwater harvesting technology will link it to the new Terminal 1. The expansion has faced challenges, including coordination with airlines, minimizing disruption during construction, and managing costs. The city is also building its own concrete plant to produce the roughly 550,000 square meters expected to be used at JFK. That's enough to fill about 218 Olympic swimming pools. Despite several hurdles, the project remains on track, with completion expected by 2030.
Next up, we have to talk about the Fangchenggang Nuclear Power Plant Megaproject. This plant plays a pivotal role in China's growing nuclear energy program and is expected to have 6 reactors when fully completed, with an estimated total output of 6 gigawatts. The project is being developed in phases, with Phase 1 comprising 2 CPR-1000 pressurized water reactors, and Phase 2 introducing China's advanced Hualong 1 reactors. Phase 1 of construction began in 2010, with the first concrete pour for Unit 1 in July. This phase featured the construction of 2 reactors, each with a net electrical capacity of 1.08 gigawatts, using Generation 2 CPR-1000 reactor technology. These reactors became fully operational in 2016, generating significant power for the region and marking the first large-scale nuclear plant in Western China. The most notable advancements came with the Phase 2 development, which includes Units 3 and 4. These reactors are based on Hualong 1 technology, a design developed by China General Nuclear Power Group. This reactor design boasts increased safety measures, a longer operational life of 60 years, and a higher output capacity compared to earlier models. Each HBR-1000 reactor produces 1.18 gigawatts of power. One of the most critical engineering elements of the Fangchenggang plant is the nuclear island construction. This section houses the reactor core and primary cooling systems, and its construction is subjected to extremely stringent quality control and testing. The reactor buildings are designed to withstand both external impacts, such as earthquakes, and internal issues, including coolant failures. The plant lies in a region that is seismically active, so earthquake resilience was a major factor in the design. Seismic isolation systems were integrated into the foundations of the reactors, with flexible base isolators allowing for the structures to move independently of ground motions during an earthquake, thus reducing potential damage. A key part of the construction process was the establishment of cooling water intake and outfall systems. Given the plant's proximity to the coast, seawater is used in the secondary cooling loop, providing a reliable and efficient way to remove heat from the power generation process. The intake structures were built offshore and connected to the plant through large underground pipelines. These intake systems had to be carefully designed to minimize environmental impact and ensure a continuous supply of cooling water. Fangchenggang also integrated digital control systems into the reactor operation, a key advancement in modern nuclear technology. These systems offer enhanced precision in monitoring reactor parameters, regulating coolant flow, and ensuring the reactors maintain optimal operational conditions. They also provide real-time diagnostic tools that can detect potential issues before they develop into major problems. The construction of the Fangchenggang plant was affected by the pandemic, which led to the delays in the commissioning of Units 3 and 4. Originally scheduled for operation by 2019 and 2020, respectively, Unit 3 achieved first criticality in December 2022, and its connection to the grid followed in January 2023. The commercial operation of Unit 3 was confirmed after it completed a 168-hour trial run in March 2023. When all 6 units are complete, the plant is expected to generate more than 34.5 terawatt-hours of electricity annually, enough to meet the energy needs of approximately 5.87 million people. The use of nuclear power at this site will prevent the release of around 28.56 million tons of carbon dioxide annually, significantly contributing to China's goal of reducing greenhouse gas emissions.
One of China's proudest achievements are their bridge construction projects. Therefore, we're paying a visit to the Qingshuihe River Bridge. Officially completed and open to the public in 2019, This architectural marvel spans the Qingshuihe River in Guizhou Province, seamlessly connecting the cities of Zhishui and Guilin. The bridge is part of a broader initiative to improve transportation links in the mountainous regions of southwest China, significantly reducing travel time between these cities from over an hour to just a few minutes. The Qingshuihe River Bridge is noteworthy for its status as one of the highest bridges in the world. It rises approximately 304 meters above the river, with a total length of 1280 meters, making it a significant achievement in China's bridge construction. The bridge's design follows a rigid frame type, with a span configuration that includes a large central span flanked by smaller approach spans, a design choice that optimizes both the structural integrity and the aesthetic appeal of the bridge. Construction of the Qingshuihe River Bridge was a monumental task that required precise planning and execution. The project's total cost amounted to $236 million, a reflection of the extensive resources, labor, and materials invested into its realization. The construction phase involved the use of cutting-edge machinery and technologies, including high-strength concrete and steel, to ensure the bridge's ability to withstand the environmental challenges presented by its location. One of the most challenging aspects of the bridge's construction was the terrain of the Qingshuihe River Valley itself. The steep and uneven landscape necessitated innovative construction methods, including the use of advanced cable crane systems to transport materials across the valley. Throughout the construction process, emphasis was placed on environmental conservation and minimizing the impact on the surrounding ecosystem. Measures were implemented to protect the river and its banks from construction-related damage, showcasing a commitment to sustainable engineering practices. Venture west to the Red Sea coast of Saudi Arabia, and you'll discover the Yanbu Industrial City project. Nestled in Al Madinah province, this sprawling city spans over 185 square kilometers, making it one of the largest industrial zones in the world. What was once a sleepy port town has transformed into an advanced manufacturing hub that powers Saudi Arabia's economy, all thanks to the visionary Yanbu project. The city was conceived to diversify Saudi Arabia's economy away from oil exports, focusing on high-value products like petrochemicals, plastics, and fertilizers. The refinery, with a processing capacity exceeding 400,000 barrels per day, serves as the backbone of the city, producing a range of refined products for global markets. Meanwhile, the nearby petrochemical complex hosts multinational companies producing billions of dollars worth of plastics, polymers, and chemicals. Building this city required a gargantuan investment of nearly $20 billion, involving meticulous planning and global expertise. Construction included over 1,000 kilometers of pipeline networks to supply oil and other utilities throughout the city. Advanced port facilities were constructed to handle millions of tons of raw materials and finished goods, including dedicated terminals for oil tankers and liquefied natural gas carriers. Despite the high ambitions, the construction faced considerable challenges due to the remote desert environment. To supply the city's water demands, engineers built the world's largest seawater cooling and desalination plant, ensuring a steady flow of fresh water to industries and residents. Additionally, a high-speed highway and rail network connects Yanbu to major cities like Jeddah and Riyadh, linking it to Saudi Arabia's extensive logistics network. With a workforce of over 50,000 skilled laborers and technicians, Yanbu Industrial City now houses more than 300 companies and continues to attract global investments. Next up, it's time to shift our focus to Italy and delve into the ambitious Terzo Valico dei Giovi project. Located in the northwestern region of Italy, this high-speed rail line is designed to connect the city of Genoa with the broader European network, significantly improving freight and passenger transport across the region. The project began construction in 2013 and is expected to be completed by 2026. This project is part of the broader Trans-European Transport Network, which aims to integrate European rail systems and boost economic growth by improving transportation efficiency. The total investment for this project is estimated at over $7 billion. The new rail line will stretch approximately 33 miles, featuring a series of tunnels that make up over 70% of the route. These tunnels, including the Valico Tunnel, which alone spans 17 miles, are designed to traverse the rugged Apennine Mountains, reducing travel times and creating a more direct route between Genoa and the Po Valley. Constructing these tunnels has presented significant engineering challenges. The project involves boring through complex geological formations, which require advanced drilling techniques and meticulous planning. Tunnel boring machines are being used to ensure precision and safety, cutting through rock while minimizing disruption to the surface above. One of the project's primary goals is to enhance freight transport between the port of Genoa and northern Italy, as well as other European destinations. The port of Genoa is one of Italy's busiest, and the Terzo Valico dei Giovi will facilitate the movement of goods by providing a faster and more efficient rail link. In addition to freight, the new rail line will significantly improve passenger travel. Currently, journeys between Genoa and Milan can take over an hour and a half by train. Once the Terzo Valico dei Giovi is operational, this travel time will be reduced to approximately 50 minutes. But the underwater megaprojects can get much longer than that. The Baltic Pipe project was completed in 2022 at a cost of approximately 1.6 billion euros, and it stretches over 900 kilometers, forging a direct link between Norway's gas fields and Poland, with passages through Denmark. Its primary aim is to diversify energy sources and reduce Central and Eastern European countries' dependence on Russian gas, showcasing a pivotal shift towards sustainable and secure energy supplies. The construction of the Baltic Pipe involved laying underwater pipelines across the North Sea and the Baltic Sea, a challenging endeavor that required advanced engineering techniques. Specialized ships were deployed to lay the pipes on the seabed, ensuring minimal disruption to commercial navigation routes. This project is notable not just for its engineering achievements, but also for its role in enhancing political cooperation among European nations. By providing a stable, reliable source of natural gas, the Baltic Pipe supports Europe's goals of energy independence and sustainability, relying less on Russia's Nord Stream pipe. It's time.
The Shenzhen Ping-An Finance Center, reaching 1,965 feet, is one of the tallest buildings globally, designed as an engineering marvel with the goal of pushing structural limits. The building began construction in 2010, with the project reaching completion in 2017 at an estimated cost of 1.5 billion. The primary engineering challenge in constructing this super-tall skyscraper involved addressing its slender profile. With a height-to-width ratio of 10:1, the building had to contend with both strong wind loads and seismic forces, typically the region's climate and geology. The Ping-An Finance Center is located in Shenzhen, which frequently experiences typhoons. This required the building to be highly wind-resistant, while also maintaining stability during potential seismic events. The structural system used in the Ping-An Finance Center is a composite system combining reinforced concrete and structural steel. The core of the building, which houses the elevators, stairwells, and other essential services, is made of high-strength reinforced concrete. The core extends throughout the entire height of the building and is crucial for resisting vertical and lateral loads. The core is also connected to the building's 8 super columns, which are spaced evenly around the perimeter of the building to help transfer loads from the top of the tower to the foundation. These columns, made from reinforced concrete at the base and transitioning to high-strength steel at higher levels, were engineered to manage both vertical and lateral forces effectively. The foundations of the Ping-An Finance Center were a critical part of the construction process due to the soft soil conditions in Shenzhen. Engineers employed deep pile foundations, driving piles over 200 feet into the ground to reach a stable layer. These piles were made of reinforced concrete, designed to support the immense weight of the building and provide resistance against lateral forces caused by wind and seismic activity. The foundation system also had to manage the building's weight, which totals approximately 1.37 million tons, to ensure even settlement across the entire footprint of the structure. The superstructure, which rises from this foundation, was constructed using a jump-form system. This method allowed for the rapid construction of the building's core, enabling engineers to pour concrete in a continuous process. The concrete used in the core was a high-strength mix, essential for resisting the significant forces placed on the building due to its height. Each new floor was completed using prefabricated steel elements, which were lifted into place using cranes. The precision required for this process was crucial, as any deviation in alignment could affect the overall stability of the building. A challenging aspect of the project was addressing the lateral forces imposed on the building by wind. At its full height, the Ping-An Finance Center is exposed to strong winds from all directions, especially during typhoon season. To mitigate this, the building was designed with an aerodynamic shape that reduces wind resistance. The cladding of the building, made from stainless steel and glass, was also tested extensively to ensure that it could withstand wind speeds of up to 125 miles per hour. Additionally, tuned mass dampers were installed near the top of the building to reduce sway. These dampers are large weights that move in opposition to the building's motion, helping to reduce the sensation of swaying during high winds or minor earthquakes. Another significant engineering challenge involved the elevator systems. The Ping An Finance Center is equipped with 33 double-deck elevators, capable of reaching speeds of up to 33 feet per second. The design of the elevator system was particularly complex because of the building's height and the need to transport thousands of occupants efficiently throughout the tower. The elevators were designed to minimize wait times and maximize efficiency, utilizing modern dispatch systems that group passengers heading to similar floors. The design of the Ping An Finance Center includes 5 underground levels, which provide space for parking and mechanical systems. This basement was built using a top-down construction method, allowing the above-ground superstructure to be built simultaneously with the excavation of the basement. This method helped to speed up the construction process while maintaining the stability of the surrounding area. The final touch of the building was a pyramid-shaped structure at the top, which completed the architectural design. Initially, the building was planned to include a spire that would have brought its height to over 2,000 feet, but this was removed from the design due to concerns about flight paths over Shenzhen. Despite this change, the Ping An Finance Center remains the second tallest building in China and one of the tallest in the world.
Next up, we have to travel to the heart of the Middle East. Where Qatar meets the Persian Gulf lies the Lusail City project, a shimmering new jewel that's redefining the concept of urban living. This master-planned city, just 15 kilometers north of Doha, is an ambitious mega-development designed to host over 200,000 residents and countless visitors. With its completion cost estimated at a staggering $45 billion, Lusail City is the embodiment of Qatar's vision for the future. Spread across 38 square kilometers, the city houses 4 distinctive districts, each offering a unique experience. From its iconic Lusail Marina to the iconic Qatar Towers, this city pulses with innovation and sophistication. One of the crown jewels of Lusail City is the Lusail Stadium, capable of hosting over 80,000 spectators, and it served as the center stage for the 2022 World Cup final. But Lusail City isn't just about iconic structures. Its urban planning integrates over 22 luxury hotels, numerous parks, promenades, and sustainable energy infrastructure that helps it achieve carbon neutrality goals. By tapping into cutting-edge construction techniques like modular steel framing and precast concrete panels, engineers ensured rapid and efficient building processes. The challenges of building in the harsh desert climate demanded innovative solutions like smart water management and temperature-controlled walkways, making Lusail a year-round haven. Despite pandemic-related delays and logistical challenges, Lusail City moved forward with a steady pace, aiming to fully realize its vision by 2025. The city's network of bridges and roadways extends over 30 kilometers, linking it directly to Doha through the Lusail Expressway and a new state-of-the-art tram network. The light rail system, which encompasses 25 stations across 4 lines, ensures seamless connectivity while reducing carbon emissions by diverting traffic away from private vehicles. Let's head to France to explore the Flamanville nuclear reactor project. Located in the Normandy region, the Flamanville 3 reactor is part of the larger Flamanville nuclear power plant, which already includes 2 operational reactors. Construction on the Flamanville 3 reactor began in 2007. This project is a flagship for the European pressurized reactor technology, developed by Framatome and Électricité de France. The EPR is an advanced design aimed at increasing efficiency and safety in nuclear power generation. However, the road to completion has been anything but smooth. Originally slated to be operational by 2012, the project has encountered numerous delays and cost overruns. The estimated cost of Flamanville 3 has ballooned from an initial $3.3 billion to over $13 billion. This makes it one of the most expensive nuclear projects in Europe. The delays have primarily been due to stringent safety requirements, technical challenges, and regulatory changes, each adding layers of complexity to an already intricate project. Flamanville 3 is designed to generate approximately 1,630 megawatts of electricity, enough to power about 1.5 million homes. The reactor utilizes EPR technology, which features a double-layered containment structure to prevent radiation leaks and a core catcher to contain the reactor core in the event of a meltdown. One of the major engineering challenges of the Flamanville 3 project has been the quality control of materials and construction. For example, in 2015, it was discovered that some of the steel components in the reactor vessel had higher carbon content than specified, potentially affecting their strength and safety. This required extensive testing and, in some cases, replacement of parts, further delaying the project. Despite these setbacks, significant progress has been made. The reactor building, towering over 200 feet high, houses the most advanced nuclear technology available. The control room is equipped with cutting-edge systems to monitor and manage reactor operations in real time, ensuring the highest standards of operational safety. The project is now estimated to be completed by mid-2024. But Japan is arguably even better at constructing underwater tunnels because they constructed the much longer Seikan Tunnel. Stretching 54 kilometers with a staggering 23 kilometers lying under the seabed, it connects the islands of Honshu and Hokkaido, piercing through the Tsugaru Strait. Completed in 1988 after nearly 2 decades of construction, the tunnel resolves the overcoming of geographical isolation and enhances connectivity. With an overall cost of approximately $3.6 billion, the Seikan Tunnel's construction presented formidable hurdles, including dealing with the seismic volatility of the region.
Let's move over to New York for the gigantic 2nd Avenue subway project. This heavily delayed development is now a reality that significantly enhances public transit in New York City. With a price tag of over $4.5 billion for its first phase alone, this project is among the most ambitious and expensive transit ventures in America. The 2nd Avenue subway has been on the drawing board since the 1920s. Financial challenges, political hurdles, and engineering complexities repeatedly stalled the project. After decades of setbacks, Phase 1 finally opened in January 2017. This marked the first major expansion of the subway system in New York City in over 50 years. The initial phase added 3 new stations along 2nd Avenue at 72nd, 86th, and 96th Streets. It has extended the Q train to provide service to the Upper East Side. These stations are state-of-the-art, featuring spacious platforms, elevators, escalators, and vibrant artwork. This makes them some of the most visually appealing ones in the system. The 2nd Avenue subway is far from complete. Phase 2, with an estimated cost of $6 billion. This will extend the line north to Harlem, adding 3 more stations at 106th, 116th, and 125th Streets. Additional phases will eventually stretch the line down to Hanover Square in Lower Manhattan. The proposed full line would be 8.5 miles and 16 stations long, serve a projected 560,000 daily riders, and cost more than $17 billion. This project has dramatically reduced congestion on the overcrowded Lexington Avenue line. This was previously the only subway serving the area. It has also improved connectivity for Upper East Side residents, cutting travel times and boosting property values in the neighborhood. The subway has boosted economic development along 2nd Avenue, attracting new businesses, residential projects, and retail establishments. It has also improved accessibility for low-income and minority communities in East Harlem, addressing long-standing inequities in transit service. Despite its successes, the 2nd Avenue subway has faced criticism for its high costs, delays, and limited scope. Each phase has taken years to plan and build, raising questions about the efficiency of large-scale transit projects in the US. In coming years, the 2nd Avenue subway will continue to transform the transit network in New York City.
It's time to travel over to Hong Kong International Airport next, also known as Chek Kok. This project was one of the most ambitious engineering projects of the late 20th century. Completed in 1998, it replaced the highly congested Kai Tak Airport, which was notorious for its location in the heart of the densely populated Kowloon area. Building this new airport involved overcoming substantial engineering challenges, particularly because it was constructed on land reclaimed from the sea. The total cost of the project reached approximately $20 billion. To create enough space for the airport, engineers had to undertake one of the largest land reclamation projects in history. The site required over 5.9 square miles of land, and this was achieved by flattening Cheklapkok Island and neighboring Lam Chau Island. The process required removing 200 million tons of earth from the islands, which was then used as a fill to create a level area on which the airport could be constructed. This fill was essential to stabilizing the soft marine clay beneath the reclaimed land, which could not have supported the weight of the airport's infrastructure on its own. The first engineering challenge was dealing with the soft seabed under the airport site. A deep foundation system had to be employed, consisting of piled foundations that reached down to solid bedrock to provide stability. Piles made of reinforced concrete were driven deep into the ground to prevent settlement and ensure that the heavy structures above, such as the passenger terminal, would not shift or sink over time. This foundation system was also necessary to protect the airport against the tides and waves, as well as potential seismic activity. The main passenger terminal was the largest enclosed space in the world at the time of completion, spanning over 600 million square feet. Its construction required innovative design solutions to ensure both durability and functionality. The terminal's roof consists of steel trusses, each weighing approximately 140 tons. These trusses were prefabricated off-site and then assembled using remote-controlled robotic cranes to lift and position them accurately. The steel structure of the roof was designed to withstand the region's frequent typhoons, which can produce wind speeds of up to 200 miles per hour. Extensive wind tunnel testing was conducted to optimize the shape of the building and ensure it could withstand the destructive forces of these storms. Another major aspect of the construction was the building of two runways, each more than 12,400 feet long. These runways had to be built on top of the reclaimed land, meaning engineers had to create a solid base that could support the weight of modern jets, including some of the heaviest commercial aircraft in the world. Connecting the airport to downtown Hong Kong was another engineering challenge. A 34-kilometer transportation corridor was built, incorporating a 6-lane expressway, 2 tunnels, and the Singma Bridge, which is one of the largest suspension bridges in the world, at 7,550 feet. This infrastructure was critical for ensuring that the airport could handle the high volume of traffic expected once it opened. The expressway and rail links enabled passengers and cargo to move efficiently between the city and airport, contributing to its role as a global aviation hub. Water management was also crucial in the design and construction of the airport. Since the reclaimed land was susceptible to flooding, a comprehensive drainage system was installed, capable of handling large volumes of water during Hong Kong's rainy season. This system includes underground tunnels and pumping stations that divert excess water away from the terminal and runways. The construction of the airport's tunnels was another massive undertaking. These tunnels were built using precast concrete sections, each weighing up to 35,000 tons. These sections were transported by barge to the site and submerged into place on the seabed. Once installed, hydraulic jacks were used to remove temporary watertight seals, and the tunnel sections were connected, forming a continuous watertight tunnel beneath the sea. This tunnel connects the airport to the city's highway system and ensures uninterrupted traffic flow between the city and the airport. Throughout its operation and expansion, the airport has maintained its position as one of the busiest airports in the world, handling over 71 million passengers annually. It also remains the world's busiest airport for cargo thanks to its strategic location and efficient infrastructure. The continuous improvements and expansion to the airport, including state-of-the-art automated baggage handling systems and passenger transit systems, ensures that it remains a crucial gateway for global travel and trade.
It's time to move over to Bangladesh next, where the Masdar power plant stands. Set along the coastal town of Maheshkhali, this $4.5 billion megaproject is designed to be the cornerstone of Bangladesh's power infrastructure. By harnessing advanced technology and engineering prowess, the coal-fired power plant will generate 1,200 megawatts of electricity, making it one of the largest power plants in the country. Built over a sprawling 1,500-acre site, the Masdar power plant is designed with 2 ultra-supercritical coal-fired units, each capable of producing 600 megawatts. The project requires immense quantities of steel and concrete to construct not only the massive power generation units, but also a dedicated deep-sea port designed to handle large coal carriers with capacities of up to 80,000 tons. The port is crucial as it provides a direct supply line for importing high-quality coal from Australia and Indonesia. Once the coal arrives, it's stored and handled via an intricate conveyor belt system stretching several kilometers. Construction began in 2017, and they laid more than 50 kilometers of high-voltage transmission lines to connect the plant to the national grid. The plant's ultra-supercritical technology uses high-temperature, high-pressure steam cycles to achieve a thermal efficiency of over 43%, minimizing carbon emissions compared to conventional coal plants. State-of-the-art flue gas desulfurization systems scrub sulfur dioxide from the exhaust gases, reducing air pollution to comply with international standards. One of the primary challenges of this project was managing its environmental impact in the delicate coastal ecosystem. Engineers had to carefully assess the project's impact on local fisheries and mitigate potential flooding risks by building elevated embankments. Moreover, extensive mangrove reforestation and habitat restoration programs were initiated to offset the ecological disruption. The plant's location in the southeastern corner of the country strategically connects it to the Bay of Bengal. But what about the construction of the biggest train station in the Netherlands? Utrecht Central Station, originally built in 1930, has long been a crucial node in the Dutch railway network. With over 200,000 passengers passing through daily, it became evident that the station required a significant upgrade to meet modern demands. The redevelopment project, initiated in early 2000 and completed in 2016, represents a blend of innovative design and practical enhancements. The station's transformation involved a substantial investment of around $1 billion, underscoring its importance to the national transport network. The project focused on expanding capacity, improving passenger flow, and integrating various modes of transportation. A key feature of the redevelopment was the construction of a new, expansive station hall. This hall, characterized by its sleek, modern design and extensive use of glass, provides a bright and welcoming space for travelers. The new station includes widened platforms and additional tracks to accommodate more trains, reducing delays and improving efficiency. Sustainability was a cornerstone of the Utrecht Central Station redevelopment. The project incorporated numerous eco-friendly features, such as energy-efficient lighting, solar panels, and advanced climate control systems. Green roofs and rainwater harvesting systems have been implemented to reduce the station's environmental footprint. The station is now a multimodal transportation hub, integrating various forms of transport seamlessly. A new bus terminal and extensive bicycle parking facilities have been added, encouraging the use of public transport and cycling over cars. The integration of these different modes of transport not only enhances connectivity, but also supports the city's goals of reducing traffic congestion and promoting sustainable urban mobility. One of the most striking elements of the project is the Hugh Cathrani shopping mall, which connects directly to the station. This modern retail complex offers a wide range of shops, restaurants, and services, turning the station area into a vibrant commercial hub. It's time to travel back to Norway for another incredible underwater project. The Oslofjord Tunnel serves as a vital link beneath the waters of the Oslofjord, connecting the regions of Østfold and Buskerud. Completed in 2000 at a cost of around $84 million, this underwater tunnel significantly reduces travel time between Oslo and the cities on the fjord's eastern side, fostering economic and social integration in the area. Spanning 7,306 meters, it is one of the longest underwater road tunnels in Norway, with a descent reaching 134 meters below sea level at its deepest point. The construction of the Oslofjord Tunnel was a complex engineering challenge, requiring the use of a drill and blast technique to carve through the rock beneath the fjord. Safety features within the tunnel, such as comprehensive ventilation systems and emergency exits, are paramount, reflecting Norway's commitment to road safety. Its construction underscores the balance between technological advancement and environmental stewardship, embodying Norway's approach to sustainable development. Now let's move to an underwater project that does not yet exist, and that would break many records if it was being constructed. The transatlantic tunnel, connecting New York to London, is a testament to human ambition and engineering prowess. But the
Hudson Tunnel project is arguably even more impressive. which will upgrade some of the most critical infrastructure in America. Beneath the Hudson River lies a vital rail connection between New York and New Jersey. This connection serves over 200,000 daily commuters, making it a lifeline for the Northeast Corridor. The project, part of the Gateway program, aims to modernize these aging tunnels and secure the future of rail travel. The first component is the construction of a new two-track tunnel. This tunnel will run from the Bergen Palisades in New Jersey to Manhattan. It is designed to add capacity and create redundancy in the system. The second component involves the final phase of the Hudson Yards concrete casing. This section will ensure uninterrupted rail access to Penn Station. The third component is the rehabilitation of the existing North River Tunnel. This tunnel, damaged during Superstorm Sandy in 2012, will be restored to modern standards. Construction is a massive undertaking involving advanced machinery and precise engineering. Tunnel boring machines will carve through the dense rock beneath the Hudson River. High-capacity cranes will assist in laying massive concrete segments for the tunnels. Specialized rail laying machines will ensure smooth track installation. This process ensures the tunnels are built to withstand modern demands and extreme weather. The new tunnel is set for completion before the rehabilitation of the existing one begins. This strategy minimizes disruptions while maintaining service for commuters. By 2035, the project aims to provide 4 fully operational tracks beneath the Hudson River. The benefits are transformative. The project will eliminate a single point of failure in the rail network. It will create over 95,000 jobs during construction, boosting the local economy. An estimated $19.6 billion in economic activity will be generated throughout the project's life cycle. The new system will also reduce road congestion, cutting greenhouse gas emissions by 2 million tons annually. This is the equivalent of flying 2.6 million people from New York to San Francisco. The Pennsylvania Railroad began design and construction work of the existing North River Tunnel in February 1903. It was opened to revenue service in November 1910. The two-track North River Tunnel was state-of-the-art in the early 20th century. However, its age and design limitations now hinder reliability. In 2012, Superstorm Sandy worsened these issues, flooding the tunnel and causing lasting damage. The Hudson Tunnel project addresses these challenges, ensuring safe and efficient travel for generations.
The Shanghai Maglev train is a revolutionary project in the field of transportation, representing the world's first commercially operated high-speed magnetic levitation system. Officially opened in 2004, the Maglev connects the Longyang Road station on the outskirts of Shanghai with the Pudong International Airport, covering a distance of 30.5 kilometers in just 7 minutes and 20 seconds. The construction and engineering behind the Shanghai Maglev train are immensely complex, as the technology it utilizes is fundamentally different from the traditional rail systems. The Maglev technology, originally developed by German companies Transrapid and Siemens, allow the train to float above the track using electromagnetic forces. This eliminates mechanical friction between the train and track, enabling extremely high speeds and smooth operation. The Maglev operates using a sophisticated system of magnets for both levitation and propulsion. The core principle relies on the electromagnetic suspension, where powerful electromagnets are installed both on the underside of the train and along the track. The magnets create a magnetic field strong enough to lift the train about 10 millimeters above the guideway. One of the critical engineering components of the Shanghai Maglev is the guideway, which is unlike traditional rail tracks. The guideway consists of a series of concrete beams embedded with coils of wire. These coils are part of the linear motor system that propels the train forward. The construction of the guideway involved significant challenges due to the need for extreme precision. Since the train hovers just a few millimeters above the guideway, any misalignments or imperfections in the track could cause operational failure or safety risks. Therefore, the guideway's concrete beams were prefabricated in a controlled environment and then assembled with laser-guided precision to ensure that tolerances were within millimeters. The beams were supported by pylons spaced 25 meters apart, which were driven deep into the ground to provide a stable foundation. The construction of the Maglev line also faced geographic and environmental challenges. The route passes through areas with soft soil, which poses risks for settlement and instability in the track. To address these issues, engineers used deep pile foundations for the pylons supporting the guideway, driving them 40 meters into the ground to reach stable soil layers. The stations on the Shanghai Maglev route were also specially designed to handle the unique characteristics of the Maglev system. Longyang Road Station and Pudong Airport Station were built with elevated platforms to match the height of the train, allowing for seamless boarding and disembarking. The project's guideway were designed to withstand earthquakes, typhoons, and other natural disasters common in the region. Sensors are embedded throughout the system to detect seismic activity, and in the event of an earthquake, the system can automatically stop trains and initiate emergency protocols. The project was built in just over 2 years, with construction beginning in March 2001 and the first test runs conducted in December 2002. During this time, thousands of workers were involved in the assembly of the guideway, installation of electrical systems, and construction of the stations. Despite the tight schedule, the project was completed on time and within the budget, thanks to the use of prefabrication and efficient project management.
Let's journey into the heart of India's infrastructure transformation with the Delhi-Mumbai Industrial Corridor, a colossal megaproject that stretches across 1,500 kilometers from the political capital of Delhi to the financial powerhouse of Mumbai. Designed to catalyze economic development and propel the nation into the next era of industrialization, the project is a multi-billion-dollar venture, pegged at around $100 billion. Envisioned in 2006, this corridor is about more than just a highway or railway. It's a blueprint for creating new economic centers, special investment regions, and smart cities. The construction of the corridor is nothing short of Herculean. Over 1,500 workers are busy laying the groundwork for an integrated transport system that includes a 1,500-kilometer-long western dedicated freight corridor. This electrified double-track rail line can handle heavy loads, enabling trains to zip goods from Delhi to Mumbai at speeds up to 100 kilometers per hour. The DFC alone is projected to reduce freight travel time by over 60%, bringing logistical costs down and improving competitiveness. Besides the rail network, the project will host over 2,000 kilometers of highways, 6 new airports and seaports, connecting industrial clusters to the world. The construction challenges are manifold. Negotiating with thousands of landowners, integrating infrastructure across 6 states, and managing the environmental impact required a delicate balance of diplomacy and precise planning. Delays from land acquisition to financing hurdles have pushed back some milestones, yet the project continues to forge ahead. When compared to similar global initiatives like the European Union's Trans-European networks, this project stands out for its blend of industrial growth and urbanization. The corridor aims to unlock the potential of over 180 million people across these regions, aiming to contribute over $1 trillion to India's GDP once fully operational. Let's shift our focus to Norway and delve into the fascinating Snøhvit LNG project, an ambitious energy initiative set in the Arctic region. Located in the Barents Sea, this project is Norway's first liquefied natural gas development, representing a significant leap in the country's energy capabilities. The project began with the discovery of the Snøhvit gas field in 1984. It took nearly 2 decades of planning and development before production finally commenced in 2007. This groundbreaking project is notable for its remote location and the challenges associated with Arctic conditions. One of the most remarkable aspects of the Snøhvit project is the decision to construct the LNG processing facilities onshore on Melkoya Island, near the town of Hammerfest. Natural gas extracted from the Snøhvit field is transported through a 90-mile subsea pipeline to Melkoya, where it is processed and cooled to -260 degrees Fahrenheit to be converted into liquid form. The total cost of the Snøhvit project is estimated at around $8 billion. The onshore facility on Melkoya includes Europe's largest LNG liquefaction plant, which has the capacity to produce nearly 5.7 million tons of LNG annually. This facility also includes storage tanks, loading berths, and other essential infrastructure, making it a comprehensive and self-sufficient operation. The plant on Melkoya employs cutting-edge technologies to reduce emissions and energy consumption. One notable feature is the carbon capture and storage system, which captures CO2 from the natural gas and injects it back into a reservoir beneath the seabed, preventing it from entering the atmosphere. Despite its successes, the Snøhvit project has not been without challenges. The harsh Arctic climate, with its extreme cold and long periods of darkness, poses unique operational difficulties. Ensuring the safety of workers and maintaining the integrity of equipment in such conditions require rigorous planning and robust engineering solutions. In addition to its technical achievements, Snøhvit LNG has strengthened Norway's position in the global energy market. The LNG produced at Melkoya is exported to various countries, including those in Europe and Asia, enhancing energy security and providing a cleaner alternative to coal and oil. This project has also paved the way for future Arctic developments, showcasing the feasibility and benefits of harnessing resources in remote locations. But what about
The Pearl River Tower in Guangzhou is considered one of the most energy-efficient skyscrapers in the world. Standing at 1,016 feet tall, the tower incorporates a multitude of advanced engineering techniques aimed at reducing energy consumption and making the building more resilient to environmental stresses. A critical component of the tower's design is its double-skin facade, which plays a key role in regulating the building's temperature and reducing its energy consumption. The outer layer of the facade allows sunlight to enter, while the inner layer helps to prevent heat from escaping. Between these two layers is a ventilation corridor, which creates natural airflow that helps cool the building during hot months and retains heat during cooler seasons. The tower's shape was meticulously designed to channel wind through wind turbines integrated into the structure. These turbines are located on two mechanical floors, where large openings in the buildings allow air to pass through, increasing wind velocity and driving the turbines more effectively. The turbines generate renewable energy that helps power the building, reducing its reliance on external electricity sources. The structure's core and shell were engineered with both seismic and wind resistance in mind. The tower's height and slender profile made it vulnerable to wind loads and lateral forces, so engineers incorporated a reinforced concrete core that houses the elevator shafts, stairwells, and mechanical systems. This core acts as the backbone of the building, providing stability against lateral forces and ensuring the structural integrity of the tower. To further enhance its resistance to seismic events, the building uses high-performance steel in the frame, allowing it to flex slightly during an earthquake without compromising its structural integrity. The foundation of the Pearl River Tower was a major engineering challenge, given the soft soil conditions typical in Guangzhou. The tower rests on a mat foundation, a type of deep foundation that spreads the building's load across a wide area to prevent uneven settlement. Engineers drilled over 150 deep piles, each more than 80 feet long, into the ground to anchor the building securely. These piles were made from high-strength concrete and reinforced with steel to ensure that they could bear the tower's immense weight while withstanding the area's frequent seismic activity. The construction process was complex due to the cutting-edge technologies and systems being implemented. The curtain wall system, which consists of high-performance glass panels, was manufactured off-site and installed using cranes to ensure precise placement. The glass is triple glazed, further enhancing the building's insulation properties and helping to maintain a stable indoor temperature. This curtain wall system not only provides thermal insulation, but also helps to minimize noise pollution, making the interior spaces quieter and more conducive to work. The elevators in the Pearl River Tower are among the fastest in the world, traveling at speeds of up to 29 feet per second. These elevators use regenerative braking technology, which captures the energy generated when the elevators descend and feeds it back into the building's power system. This technology reduces the overall energy consumption of the elevators by up to 30%, further contributing to the building's energy efficiency.
Let's explore the Pont de Normandie in France, a marvel of modern engineering that elegantly spans the Seine River, connecting the cities of Le Havre and Honfleur. This iconic bridge, completed in 1995, stands as one of the longest cable-stayed bridges in the world. The Pont de Normandie stretches an impressive 7,032 feet, or approximately 1.33 miles. Its most striking feature is its central span, which measures 2,808 feet, supported by two soaring pylons that rise 656 feet above the Seine. These pylons, constructed from reinforced concrete, are designed to withstand strong winds and seismic activity, ensuring the bridge's stability and longevity. Construction of the Pont de Normandie began in 1988 and took 7 years to complete. The project was a significant undertaking, costing around $465 million. One of the engineering highlights of the Pont de Normandie is its use of cable-stayed technology, which allows for longer spans and greater flexibility compared to traditional suspension bridges. The bridge's deck is supported by a series of cables that fan out from the pylons, creating a visually stunning and structurally efficient design. The bridge's roadway consists of 4 lanes, 2 in each direction. The bridge has reduced travel time between Le Havre and Honfleur to just a few minutes, enhancing economic activities and fostering closer ties between the two cities. Architecturally, the Pont de Normandie is celebrated for its elegant and minimalist design, which complements the surrounding landscape. Its sleek lines and towering pylons make it a landmark that is both functional and aesthetically pleasing. The bridge has won numerous awards for its design and engineering, including the Outstanding Structure Award from the International Association for Bridge and Structural Engineering in 1995. The construction of the Pont de Normandie involved innovative techniques and meticulous planning. Engineers had to address several challenges, including the strong winds typical of the region and the need to maintain river traffic during construction. The use of precast concrete segments assembled on site allowed for precise construction and minimized disruptions. Each segment, weighing up to 200 tons, was carefully positioned and secured, ensuring the structural integrity of the bridge. The economic impact of the Pont de Normandie extends beyond improved transport links. It has become a tourist attraction in its own right, drawing visitors who marvel at its design and the panoramic views it offers. Moreover, the Pont de Normandie has played a vital role in regional integration within the European Union. By improving transport links between France and its northern neighbors, the bridge facilitates smoother and more efficient movement of goods and people across borders. While that tunnel might be long, it's time to visit a tunnel that's over 10 times as long. The Channel Tunnel, an engineering feat that bridged the UK and France beneath the English Channel, stands as a symbol of European unity and technological ambition. Completed in 1994 at a cost of £12 billion, this project was one of the most significant engineering projects of the 20th century. Spanning 50.45 kilometers, with 37.9 kilometers beneath the sea, the Channel Tunnel holds the record for the longest undersea portion of any tunnel in the world. The construction involved the use of 11 tunnel boring machines to carve through the chalk marl beneath the seabed. This Herculean task required unprecedented coordination between British and French construction teams. The tunnel comprises 3 separate tubes, 2 for rail traffic and a smaller service tunnel that acts as an emergency escape route. The use of precast concrete linings to reinforce the tunnel walls was a critical component of the construction strategy, ensuring the tunnel's durability and safety. Today, the Channel Tunnel is a vital link for commerce and travel between the UK and continental Europe, facilitating the seamless transit of millions of passengers and tons of freight annually. But let's investigate the Tokyo Bay Aqua Line project next, which is located in Japan. This innovative megaproject, completed in 1997 after almost a decade of construction and costing nearly $11 billion, spans 15.1 kilometers and merges the infrastructure of both tunnel and bridge into a seamless transport artery. The Aqua Line begins with a 4.4-kilometer bridge stretching from Kawasaki and transitions into a 9.6-kilometer undersea tunnel, making it the world's 4th longest one. The 2 sections meet at an artificial island known as Yumiharu, a 650-meter diameter structure that serves as both a ventilation shaft and an entertainment complex. A project of this magnitude presented considerable engineering challenges. To manage the underwater construction, the teams utilized the world's largest shield tunneling machines, which bored through the seabed while simultaneously reinforcing the walls with high-strength concrete segments. The tunnel was divided into several watertight sections to minimize flooding risks. Meanwhile, constructing the bridge required innovative solutions to address seismic concerns, given Japan's notorious earthquakes. Engineers designed flexible bridge piers to withstand tremors, while shock absorbers were embedded in the structure to minimize damage. The project's complexity also meant securing permits from multiple government agencies while ensuring minimal impact on the marine ecosystem. The result is a structure that has drastically shortened the travel distance between Kawasaki and Kisarazu by over 70 kilometers. In terms of size, the Tokyo Bay Aqua Line is comparable to almost 200 football fields and handles around 32,000 vehicles daily.
The Bapanjiang Bridge, completed in 2016, is a monumental structure that spans 4,400 feet across the Baipan River Valley in Guizhou, China. It is an engineering marvel not only for its extreme height, standing at 1,854 feet above the river, but also for its complex design and construction. A critical aspect of the bridge's construction was its location in the mountainous region of Guizhou, which presents extreme geological and environmental challenges. The construction site is situated in a remote area with steep cliffs and limited accessibility, making it difficult to transport materials and equipment. Engineers had to develop innovative methods to bring construction materials to the site. A key solution involved building temporary access roads to deliver materials and equipment to the top of the cliffs, where the bridge towers would be erected. The foundation of the bridge had to be exceptionally robust to support the weight of the bridge and withstand the forces of wind, seismic activity, and heavy traffic. The towers, which rise over 656 feet from the base of the gorge, require deep foundations to anchor them into the unstable rock strata beneath the surface. To achieve this, engineers employed piled foundations with piles driven over 130 feet into the ground. These piles were reinforced by high-strength steel and concrete to ensure that they could support the enormous loads imposed by the bridge's weight and the tensions of the cables. One of the key challenges during the construction phase was erecting the massive towers that would support the bridge's cables. These towers were constructed using a jump form system, a method where sections of the tower are poured and then the framework is raised to pour the next section. This method allows for precise control over the height and alignment of the towers and ensures that the structure remains stable during construction. Given the height of the towers and the challenging environmental conditions, the formwork had to be specially designed to withstand high winds and temperature fluctuations. The bridge's deck was constructed using steel box girders, which are hollow steel structures that provide high strength while minimizing weight. These girders were prefabricated off-site to ensure quality control and then transported to the construction site where they were lifted into place by cranes. The steel box girders were chosen for their ability to span long distances without the need for intermediate supports, which was critical given the depth of the gorge. The girders were welded together to form a continuous deck, and additional steel reinforcement was added to ensure that the deck could support the weight of the traffic above. Wind resistance was a significant factor in the design of the Bapanjiang Bridge, given its height and location in a mountainous region prone to strong winds. To ensure the stability of the bridge under high wind conditions, engineers conducted extensive wind tunnel testing to study the effects of wind on the structure. The results of these tests informed the design of the bridge's towers and deck, which were optimized to reduce wind load and minimize potential for vibrations. Additionally, tuned mass dampers were installed in the towers to counteract the effects of wind-induced vibrations. These dampers consist of large weights suspended within the towers that move in opposition to the vibrations, stabilizing the structure. The construction of the Bapanjiang Bridge required significant logistical coordination, particularly given the remote location and the scale of the project. Materials such as steel and concrete had to be transported over long distances to the construction site, and temporary infrastructure such as roads and bridges had to be built to accommodate this. The total cost of the Bapanjiang Bridge was estimated to be around $143 million. The project was completed in just 4 years, a remarkable achievement given the complexity of the construction and the challenges posed by the site. The bridge has transformed transportation in the region, reducing travel time between the two provinces from 5 hours to less than an hour.
It's time to talk about one of Europe's most ambitious and delayed infrastructure projects, Berlin-Brandenburg Airport, located in Germany. The idea for this aviation hub was conceived in early 1990 after the reunification of Germany. The goal was to create a single, state-of-the-art airport that would consolidate air traffic and replace the aging Tegel and Schönefeld airports. Construction began in 2006, and the project was initially scheduled for completion in 2011. However, a series of technical problems, planning errors, and safety issues delayed the opening until October 31, 2020. The total cost of Berlin-Brandenburg Airport soared to approximately $7 billion, far exceeding the original budget of around $2 billion. The airport spans a massive area of almost 14 square miles, highlighting the scale of this undertaking. One of the most significant challenges faced during the construction of Brandenburg Airport was the complex fire safety system. The automated smoke extraction system failed numerous tests, leading to extensive redesigns and delays. Additionally, issues with wiring, escalators, and security systems required significant rework and contributed to the extended timeline. The airport features 3 terminals and 2 parallel runways, designed to handle up to 46 million passengers annually. The airport's design incorporates modern architecture with extensive use of glass and steel, providing a bright and open atmosphere for travelers. The facility includes numerous energy-efficient features, such as LED lighting, a sophisticated waste management system, and extensive use of renewable energy sources. Solar panels installed on the roof of the terminals generate a portion of the airport's electricity, reducing its environmental footprint. Despite the numerous setbacks, the airport's eventual opening has been a significant milestone. The airport now serves as a major hub for both domestic and international flights, boosting connectivity for the German capital. It's time to visit the United Kingdom, where a tunnel is being constructed for an ambitious purpose. The Thames Tideway Tunnel aims to tackle London's over-a-century-old sewage system problem. Officially initiated in 2016 with an estimated completion by 2025, this massive undertaking is designed to prevent millions of tons of untreated sewage from entering the Thames River each year. Stretching over 25 kilometers and delving up to 65 meters below the river, the tunnel is a critical component of modernizing London's sewage disposal and treatment capabilities. Costing approximately £4.9 billion, the project is not just an engineering marvel, but also a significant environmental initiative. By intercepting overflow from existing Victorian sewers, the tunnel will ensure that the Thames remains cleaner and more vibrant for future generations. Despite its environmental benefits, the Thames Tideway Tunnel has faced controversy, particularly regarding its financial impact on residents through increased water bills.
But we have not talked about Sound Transit 3 just yet, which is a monumental transportation infrastructure project aimed at transforming public transit in the Puget Sound region of Washington state. With an estimated budget of $54 billion, ST3 represents one of the largest mass transit expansions in US history. The project extends the existing light rail, commuter rail, and bus rapid transit systems of the region by over 116 miles. Key elements include new light rail lines connecting Seattle to Everett, Tacoma, Ballard, and West Seattle. The project also expands Sounder commuter rail services to South King and Pierce counties and introduces bus rapid transit corridors for faster and more reliable travel. The backbone of ST3 is its light rail network, which will include 37 new stations, bringing the total to over 70. These stations will provide seamless connectivity to major employment centers, residential neighborhoods, and educational institutions. The extension to Tacoma and Everett will significantly reduce travel times, offering commuters a fast, eco-friendly alternative to driving. Light rail trains would run 20 hours per day and every 3 to 6 minutes during peak hours. The plan requires the purchase of 226 new vehicles to operate on the new lines. Sound Transit 3 incorporates advanced technologies to enhance the passenger experience. New stations will feature real-time arrival information, improved accessibility for people with disabilities, and safe, well-lit environments. Parking facilities at key stations will also be expanded to accommodate the growing demand for park and ride services. The ST3 expansion is expected to create thousands of jobs during its construction phase and stimulate economic activity in surrounding areas. By improving access to affordable housing, education, and healthcare, the project also addresses social equity. This ensures that underserved communities benefit from enhanced connectivity. The ambitious scope of ST3 presents several challenges, including budget management, environmental reviews, and community engagement. The pandemic caused delays and increased costs, prompting a re-evaluation of timelines and priorities. Despite these setbacks, major components of the project are expected to be completed by 2041, with interim phases opening earlier. Sound Transit Board has recently approved the route and station locations for the West Seattle Link extension. This action authorizes the project to move forward into the final design phase. Construction is expected to begin in 2027. By 2040, Sound Transit estimates that its services will carry a total of between 561,000 and 695,000 daily riders, with 69% of all transit trips using rail services.
Next up, we have to travel to the United Arab Emirates, where the desert sands of Abu Dhabi hold the Barakah nuclear power plant. Located in the sparsely populated Al Dhafra region, this $24 billion megaproject aims to diversify the country's energy portfolio while meeting the region's growing power needs. Construction of the power plant began in 2012, spanning a 9-square-kilometer site along the western coast. The plant comprises 4 APRA-11400 reactors, each designed to generate 1,400 megawatts of electricity. Collectively, these reactors will produce a staggering 5,600 megawatts, meeting up to 25% of the UAE's energy needs and preventing the release of 21 million tons of carbon emissions annually. That's like taking 4.5 million cars off the roads each year. With a containment dome rising nearly 60 meters above ground and the reactor pressure vessel weighing over 500 tons, each reactor stands as a colossal feat of precision engineering. The reactors are built with multi-layered safety systems, including double-walled containment structures to withstand natural disasters and external impacts. But constructing a nuclear power plant in such a region was not without its challenges. The unforgiving desert climate required innovative cooling systems to maintain optimal reactor temperatures. Advanced desalination plants were built to supply millions of liters of cooling water daily, while engineers worked tirelessly to meet stringent safety and quality standards. By bringing in global expertise, the country ensured that the project met international best practices in nuclear safety. In a part of the world where oil has long been king, the power plant is setting the standard for nuclear energy, particularly in a geopolitical landscape often defined by energy challenges. When all 4 reactors are fully operational, Barakah will produce more electricity than many countries generate in a year. It's time to turn our attention to the Netherlands and explore the ambitious Zuiderzee project, a major infrastructure initiative set to transform Amsterdam's bustling Zuiderzee district. Initiated in 2019, the project is a multifaceted endeavor aimed at upgrading the existing infrastructure in the district. With a budget of around $2 billion, this project reflects the strategic importance of Zuiderzee as a center for finance, law, and business. The project is scheduled for completion by 2028, promising to deliver significant benefits to the area and its residents. At the core of the Zuiderzee project is the expansion and modernization of Amsterdam Zuid Station, transforming it into a major transportation hub. The station will be upgraded to accommodate increased passenger volumes and to improve connectivity with other parts of the city and the region. This includes the addition of new platforms, enhanced facilities, and better accessibility, making it a central node in Amsterdam's transportation network. Another key component of the project is the widening of the A10 South Ring Road. This section of the highway, which currently experiences heavy congestion, will be expanded to improve traffic flow and reduce travel times. The construction of new tunnels will allow the highway to pass underground in certain sections, freeing up surface space for urban development and green areas. These tunnels are designed to integrate seamlessly with the existing road network, minimizing disruption while enhancing capacity. Additionally, smart traffic management systems will be implemented to optimize traffic flow and reduce congestion, making transportation in and around Zuiderzee more efficient and sustainable. Let's transition to another underwater project that is connecting cities called the Busan-Gyeonggi Fixed Link. Spanning an impressive length of 8.2 kilometers, this fixed link connects the bustling city of Busan with the scenic island of Gyeonggi in South Korea, serving as a vital artery that significantly reduces travel time. Constructed at a cost of approximately $800 million, the project was completed in 2010 after 5 years of relentless work. The fixed link is a hybrid structure, comprising both bridges and underwater tunnels, ingeniously designed to navigate the challenges posed by the area's deep waters and heavy marine traffic. The centerpiece of this engineering feat is a 3.7-kilometer immersed tunnel, one of the longest of its kind in the world, which plunges beneath the sea to allow ships to pass unimpeded above. Despite its successes, the project was not without its challenges. Environmental concerns were raised regarding the impact on the marine ecosystem, leading to stringent measures being implemented to mitigate damage. Financial obstacles also loomed large, with debates on the project's cost-effectiveness and the burden on public resources sparking rigorous discussions. Now we haven't investigated the Barmer refinery yet, located in India. This megaproject, formerly known as the Barmer Refinery and Petrochemical Complex, is being constructed in the dusty town of Pachpadra, about 60 kilometers from Barmer City. The $6 billion refinery will have a processing capacity of 9 million tons per annum, producing high-quality fuels like diesel, gasoline, and jet fuel. It also houses an integrated petrochemical complex designed to produce over 2.4 million tons of petrochemicals annually. Once operational, the facility will feed various industries across India, ranging from textiles to packaging. The refinery's strategic location will leverage the crude oil reserves found in the Rajasthan Basin, providing an efficient supply chain directly to the facility. Construction began in 2018, but this undertaking required years of meticulous planning due to the region's harsh desert climate and sparse infrastructure. The remote location posed logistical challenges, as thousands of tons of steel and cement were transported over hundreds of kilometers to reach the site. Engineers relied on specialized construction materials and corrosion-resistant coatings to protect the refinery's complex piping and machinery from desert sand and high temperatures. A crucial aspect of the refinery's design is its sustainability measures. It will feature advanced flue gas desulfurization systems, ensuring emissions are scrubbed before being released. Water is another major concern in the Thar Desert, and the refinery employs a state-of-the-art wastewater treatment plant to recycle and reuse up to 80% of its industrial water. Pipelines have been laid from faraway Gujarat to supply the refinery with the natural gas needed for power generation and feedstock. But we have to travel to France next, where the LGV Sud Europe Atlantique project represents a major leap in the country's high-speed rail network. Initiated in 2011 and completed in 2017, it extends the existing high-speed line from Tours to Bordeaux. Spanning approximately 188 miles, this new section of the line significantly reduces travel times, cutting the journey from Paris to Bordeaux to just over 2 hours. One of the most impressive aspects of the LGV project is the scale of its construction. With an investment of around $8 billion, the project involved extensive engineering work, including the construction of over 400 engineering structures such as viaducts, bridges, and tunnels. The route traverses diverse landscapes, from rolling countryside to urban areas, necessitating innovative solutions to minimize environmental impact and disruption to local communities. A notable feature of the LGV line is its advanced rail technology. The line supports trains traveling at speeds of up to 200 miles per hour, making it one of the fastest rail lines in Europe. This high-speed capability is achieved through the use of state-of-the-art track design and cutting-edge signaling systems, ensuring both speed and safety. The environmental considerations of the project were paramount. Extensive environmental impact assessments were conducted, and measures were taken to protect local wildlife and natural habitats. Additionally, the project included reforestation initiatives and the restoration of natural landscapes affected by the construction. Beyond its engineering feats, the LGV project has had a profound socio-economic impact. By dramatically reducing travel times, it has enhanced the accessibility of southwestern France, promoting regional development and economic growth. The construction phase of the project provided a significant boost to the local economy, generating thousands of jobs and supporting numerous businesses. Crossing the North Sea, it's time to visit Norway for a massive underwater megaproject. Norway's Coastal Highway project is an unparalleled infrastructure endeavor aimed at revolutionizing travel along the country's rugged western coast. With an estimated cost of $40 billion, this ambitious project seeks to eliminate the need for 7 ferry crossings by connecting the cities of Kristiansand in the south to Trondheim in the north through a continuous, ferry-free highway. Spanning over 100 kilometers, it involves the construction of bridges, tunnels, and causeways designed to navigate the challenging Norwegian underwater terrain and weather conditions. A highlight of the project is the proposed construction of the world's longest and deepest submerged floating tunnel, a feat of engineering that exemplifies Norway's innovative approach to overcoming geographical obstacles. This tunnel alone, part of the route across the Sognefjord, is expected to stretch 3.7 kilometers in length and reach depths of up to 392 meters below sea level. Scheduled for completion in 2050, the Coastal Highway project not only aims to significantly reduce travel time across the western coast, but also to boost economic growth and connectivity in remote regions. But how about the complicated construction of a major city project? In the scorching sands of Abu Dhabi, a futuristic oasis has emerged. Masdar City, an ambitious project designed to redefine urban living in one of the world's hottest climates. Located just 17 kilometers southeast of the Abu Dhabi skyline, this eco-city is the embodiment of the United Arab Emirates' vision for sustainable urban development. While initially planned to be completed by 2016, this multi-billion-dollar megaproject has adopted a phased development approach, pushing full completion to 2030. The city, costing around $22 billion and covering 6 square kilometers, is meticulously designed to optimize natural resources. Solar energy powers every facility, and a 10-megawatt solar farm at the city's perimeter generates electricity for over 4,000 households, while rooftop solar panels add to the mix. As the world's first eco-city built from scratch, Masdar City has implemented cutting-edge building materials like low-carbon concrete and high-performance glazing, significantly reducing its carbon footprint. With an anticipated population of 50,000 residents and another 40,000 commuters, Masdar City will be a buzzing hub of sustainable living. While the initial target of zero emissions is challenging, the city's progress continues, marked by innovative pilot programs for green technologies. Transport within the city is emissions-free, thanks to a personal rapid transit system featuring autonomous electric vehicles gliding along magnetic tracks, supplemented by pedestrian-friendly pathways. Challenges like fluctuating oil prices, unpredictable markets, and the pandemic have shifted its development timeline, but the city continues to be constructed until this day.
The Miami Signature Bridge is an iconic infrastructure project designed to improve traffic flow and redefine the city's skyline. With a cost of $818 million, this modern bridge combines functionality with architectural beauty. The Signature Bridge is planned as a 1025-foot-long bridge over NE 2nd Street and Biscayne Boulevard, and will redefine the skyline in Miami with 6 massive arches. The largest arch is expected to reach a height of 325 feet and be 650 feet wide. The design of the bridge includes sweeping arches illuminated by LED lights, creating a striking visual effect. It serves as a gateway to downtown Miami, connecting major highways and enhancing the aesthetic appeal of the city. The Signature Bridge is part of the I-395, SR-836, and I-95 improvement project, addressing congestion in one of the busiest corridors in Miami. By streamlining traffic flow, it reduces travel times and improves safety for drivers and pedestrians. Beyond its practical benefits, the bridge includes public spaces, pedestrian walkways, and green areas underneath. These features transform the area into a vibrant community hub, blending infrastructure with urban living. Construction has faced delays due to weather and logistical issues, but the project remains on track for completion in 2027.
Let's dive into the impressive Afsluitdijk project in the Netherlands. Originally completed in 1932, it stretches 32 kilometers across the Wadden Sea, connecting the provinces of North Holland and Friesland. It has served as a critical barrier against the North Sea, protecting the low-lying regions of the Netherlands from flooding. The current project to upgrade the Afsluitdijk began in 2018 and was completed in 2023. This renovation is essential to cope with rising sea levels and the increasing frequency of severe weather events. The cost of the project is estimated at around €550 million, reflecting the complexity and scale of the endeavor. A significant aspect of the project is the reinforcement of the dike itself. The existing structure, which has protected the Netherlands for nearly a century, is being upgraded with the installation of innovative flood defense systems. One of the key features is the addition of new sluices and pumps to manage water levels more effectively. These systems are designed to handle excess water during storms and high tides, ensuring the safety of the surrounding areas. The project also includes the construction of a new storm surge barrier. This barrier, located at the western end of the dike, will provide additional protection against the increasingly severe storms that the region faces. The barrier is designed to be both functional and visually striking, blending seamlessly with the surrounding landscape while offering robust protection against the sea. Sustainability is a core focus of the Afsluitdijk project. The renovation incorporates renewable energy sources with solar panels and wind turbines installed along the dike to generate clean energy. These installations are expected to produce enough electricity to power the new sluices and pumps, making the Afsluitdijk not only a protective structure but also a contributor to the country's green energy goals. The next project on our list is a tunnel that's connecting two major countries, the Fehmarn Belt Fixed Link. This ambitious project, with an estimated cost of 7.4 billion euros, is not just another infrastructure endeavor. It's a bold leap towards uniting regions and enhancing mobility in Europe by connecting Germany and Denmark. Spanning approximately 18 kilometers, it's poised to become the world's longest immersed tunnel, designed for both rail and road traffic. The construction employs the use of specially designed ships to lay sections of the tunnel on the seabed, a method that underscores the innovative spirit of this undertaking. The tunnel comprises 79 individual segments, each meticulously fabricated off-site, showcasing the meticulous planning and precision that underpin this colossal project. The planned completion date for this project is unknown, but they're aiming to open it somewhere in 2029. Let's talk about the incredible Genoa Bridge in Italy. Officially known as the Genova-San Giorgio Bridge, this project was initiated following the tragic collapse of the old Morandi Bridge in August 2018. Construction of the bridge commenced in April 2019 and was completed in just over a year, opening to traffic on August 3, 2020. This impressive timeline was achieved through the concerted efforts of approximately 1,000 workers who toiled around the clock. The project cost an estimated 202 million euros, reflecting the urgent need and the scale of the endeavor. The new bridge spans 1,067 meters in length, with a width of 31 meters. To put this into perspective, the length of the bridge is equivalent to nearly 11 football fields laid end to end. Its height varies, with the tallest piers standing at 45 meters, offering a majestic view over the Pulsever River. One of the key engineering challenges was the necessity to construct the bridge swiftly and safely, considering the urgency of replacing the collapsed structure that had severed a crucial transportation link in the region. The construction involved the use of advanced building techniques, such as prefabricated steel segments, which were assembled on site to accelerate the process. These segments were meticulously designed to fit together seamlessly, ensuring both structural integrity and aesthetic appeal. In terms of design, the bridge features a continuous steel deck supported by 14 reinforced concrete piers. Each pier is equipped with sensors and monitoring systems to ensure ongoing structural health and safety, a critical consideration given the tragic history associated with its predecessor. Sustainability was a key focus throughout the project. The next underwater project is going to be a lot more feasible. The Gibraltar Strait Tunnel seeks to connect Europe and Africa, specifically Spain to Morocco, through a 14-kilometer underwater rail tunnel. This endeavor not only aims to bridge two continents, but also to significantly enhance economic and cultural exchanges between them. The project, with an estimated cost that could exceed $20 billion, is a testament to the potential of modern engineering to overcome geographical barriers. Construction of such a tunnel presents formidable challenges, from the deep waters of the Strait of Gibraltar, with depths up to 900 meters, to the seismic activity in the region. The proposed tunnel would be among the world's longest underwater tunnels, dwarfing existing ones in both ambition and technical complexity. Engineers are considering innovative boring techniques and special materials to ensure the tunnel's integrity and safety, taking lessons from other underwater projects like the Channel Tunnel between France and the United Kingdom. But how about an extremely tall tower megaproject? Welcome to Kuala Lumpur, where an iconic spire pierces the sky, the Kuala Lumpur Tower. Rising 421 meters above the Malaysian capital, it's the world's seventh tallest freestanding tower and the tallest in Southeast Asia. Completed in 1995, the tower's construction spanned 4 years, transforming a forested hill into one of Malaysia's most recognizable landmarks. The tower's construction required meticulous engineering to ensure the structure could endure Malaysia's tropical climate and seismic activity. Anchored by a deep foundation reaching 17 meters below ground level, engineers poured over 50,000 cubic meters of concrete, forming the tower's base. The main structure comprises reinforced concrete, supported by high-strength steel reinforcements that run through the core. The tower's unique architectural design reflects Malaysia's Islamic heritage, with decorative arabesques and arch motifs integrated into the facade. Above the podium lies the tower shaft, which culminates in a spherical observation deck. The tower also serves as a crucial telecommunication hub, hosting transmission facilities that cater to television and radio stations, boosting signal strength across the city. Its location on Bukit Nanas means the tower's height, combined with the hill's elevation, provides a view that makes it appear taller than the Petronas Towers, even though it's technically shorter. It's time to turn our attention to Norway and uncover the impressive Hålogaland Bridge. Completed in December 2018, this remarkable structure spans the stunning Rombeksfjord near Narvik. The Hålogaland Bridge stretches an impressive 381 feet. The main span alone measures 455 feet, making it the longest suspension bridge span in Norway and the seventh longest in Europe. The height of the bridge towers reaches an awe-inspiring 607 feet, providing the necessary support for the expansive span over the fjord. Construction of the bridge began in 2013, with a total investment of around $400 million. Prior to the bridge's completion, the journey around the fjord required a lengthy detour, adding an extra 21 miles to the trip. With the bridge in place, travel distance is cut by nearly 18 miles, saving approximately 20 minutes for drivers. The bridge was designed to withstand the harsh Arctic climate, including strong winds, heavy snowfall, and freezing temperatures. Engineers employed advanced materials and construction techniques to ensure the bridge's durability and safety. The cables supporting the bridge are made from high-strength steel, capable of bearing enormous loads while maintaining flexibility. Let's travel to Chennai, the bustling capital city of Tamil Nadu, India. Here the Chennai Metro has emerged, which is rewriting the narrative of urban mobility in one of India's most dynamic cities. The project's massive scale is immediately apparent. With a total network length of 54.15 kilometers and 41 stations spanning 2 corridors, this metro system is a lifeline connecting neighborhoods and industrial areas. Constructing this network was no easy feat. With a budget of over $3 billion, the project demanded cutting-edge construction techniques. Engineers and workers overcame enormous challenges posed by Chennai's complex geology, including loose alluvial soil and high groundwater levels. The team employed advanced tunnel boring machines for the underground stretches and meticulously precast concrete segments for elevated tracks. Some stations, such as the futuristic underground government estate, are constructed at dizzying depths of up to 23 meters below ground. In contrast, the elevated stations tower above the landscape, their sleek designs ensuring accessibility for the differently abled. The entire system was designed to cater to up to 700,000 passengers daily, reducing road congestion and air pollution across Chennai. The benefits of the Chennai Metro are not only immediate but also strategic. As India's fifth largest urban agglomeration, Chennai needed an efficient transportation network to alleviate severe traffic snarls and boost economic productivity. Its sheer scale is comparable to other Asian transit networks like the Bangkok BTS. However, the Chennai Metro stands out for its ambitious Phase 2 expansion plan.